We're going to talk about electrochemistry. Now, the beginning part of electrochemistry is actually going to be a review. So I want to go over a short review here. I want to teach you about oxidation and reduction in case you forgot it or you didn't really learn it really well from Chem 1. So what is an oxidation? What is a reduction? Okay. In general, these two are separate reactions, but one cannot happen without the other. If you see an oxidation happening, reduction is also happening in that same place, reaction. You just have to look for it. So because oxidation and reduction is such a big mouthful, we just call it redox. Okay, so redox will have someone being oxidized. Well, the atom that is being oxidized will be, there's a lot of definitions. One of them is losing an electron. And then the one that gains electron is being reduced. So that's where you get the oil rig from. Oil rig means oxidation is the loss of electrons, reduction is the gain of electrons. Then remember, this is electron. Oil rig stands for electrons, not something else, which we will be learning about oxidation states after this. Okay, oil rig only talks about electrons. So you can easily see it in this example here, but sometimes electron movements are not obvious. Okay, and then the best way to do is by determining oxidation states. Electrons, you can see if it's ionic here. It's pretty easy to tell, but there are a lot of covalent compounds, molecular compounds here that we will be using, and you can't easily tell where the electron's going. So, but as an example here, sodium going to sodium ion, you lost an electron, so the electron is in the product site. So you got to remember, when I write an oxidation, the electron is the product site because it releases and it loses the electron. Whatever you lose comes out on a product site. And that's oxidation. Now, chlorine here, you have to gain 2 electrons to turn it into an anion because there's Cl2 and then you got 2 electrons and 2 Cl. So this is a reduction. So when they say oil rig means oxidation is loss of electrons, reduction is gain of electrons. Okay, there are other definitions as well, so let me show you. In general, oxidation, number 1 is, we said it loses electron. That one's what we mentioned, right? The next one is as oxidation number of element increases. So that's the one I like to teach you guys. We are going to learn how to identify oxidation numbers for every single element in every single equation, every single compound. And we're going by element, okay? If the element in the reactant side was a smaller oxidation number, and on the product side, the same element is now a bigger oxidation number, we consider the element to have been oxidized. So number oxidation state has to go up. It loses an electron, we just saw the example. And a lot of times, this is really the first indication of oxidation is you added oxygen to it, okay? If you add oxygen, generally, you might also lose hydrogen, but these are not so obvious. So this is the easiest way to determine. So we're going to be doing oxidation number. But oxidation loses electrons, add hydrogen, loses hydrogen. Add oxygen, loses hydrogen. And because it loses electrons, the electrons are on a product side. Okay? Now, on a reduction, electrons are on a reactant side. It gains electrons. The oxidation number here goes down. From the reactant side to the product side, the number actually goes down. It loses an oxygen, gains a hydrogen. So it's literally opposite. And these two cannot happen without, like one cannot happen without the other. If reduction is there, oxidation was already happening. These two have to happen together, okay? Now, there are rules now to assign oxidation state. So let's go over the rules first. The rules really are kind of hard to understand until you actually do examples. So I'm going to show you the rules here, and I'm going to repeat the rules for you every time we do some problems. We'll practice, okay? So number 1, we're going to say, if you see any freestanding elements that are by itself, free elements means the element is by itself, there's nothing else with it, it's just that one element, one thing from the periodic table, that spot. Okay, so Na by itself is an element. Cl2 is an element too because it's diatomic element and it's just Cl in there. Those are all considered free elements. So they are going to be zeros by default, okay? So Na solid, Cl2 gas are zeros because they're all elements. Now, if you see an ion, that's monatomic ion, the charge of the ion will be the same as the oxidation state, the numbers, okay? So obviously we know the charge of sodium is +1, chloride is -1, so you know the oxidation state of sodium is 1, chloride is -1, same as the state. Now, another thing you gotta remember is when you add up the oxidation states all together, like Na and Cl, it adds up to the total. If it's a neutral compound, it adds up to 0. So Na was +1, Cl was -1, it does add up to 0. Okay, so whatever the compound is, if it's neutral, it adds up to 0. If it's not neutral, it's a polyatomic ion, then it should add up to the charge of the ion. So for a nitrate here, they say N was 5, and then oxygen, each one was -2. There's 3 of them. It adds up to -1, which is perfect because that's the charge of nitrate. And then the next one is group 1 will always have +1. Group 2 will always have +2. And then you go F is always -1, H is +1, O is -2, group 7, -1, group 6, -2, group 5, -3. So these are the rules, okay? So if you have your slides, we can follow it through. But I'm going to give you some examples, and we're going to refer back to this to see how we can assign oxidation states. Again, this is stuff we should have done in Chem 1. Let's just review, okay? The reason I'm doing such a big review here is because if you can't do this part, you cannot do the rest of the chapter. It's going to be so hard. So we want to make sure you know this really, really well. Okay, so we're in chapter 20. We'll do our problem here. The first one, I want you to assign the oxidation state for Br and Br2. Remember, we're looking at the element in here, so each Br here will be what, and it adds up to what? So Br2 is a freestanding element, agree? See, free element, 0, okay? So each Br is 0, even though I got 2, they still add up to 0, so we're good. What about this guy? K plus. What's the oxidation state for K in this guy? So then you take a look at your rules, if you forgot. So you really need to memorize the rules, okay? Monatomic ions is the same state as the charge. So therefore this is +1. You guys getting the hang of this? Okay, now let's try a compound, okay? Try water. Now, I have a compound here, but you have to determine for all the elements in there. So H will have a number, O will have a number, okay? So to do this, you need to know I have 2 hydrogens plus 1 oxygen, and it equals to 0. I'm gonna drop the 1 because it looks like a 10 now. Okay? Now, the next thing you do is we know it adds up to 0 because this is a compound, it adds up to 0. Then we go through our priority list, okay? Our priority list is group 1 metal +1. Do you see group 1 metal? No. Skip. Group 2 metals is +2. Do you see group 2 metal? Nope. Skip. Okay? And then we go to F is -1. Do you see F? Nope. Skip. Do you see H? Yes, I see H. That's my first priority. H is automatically assigned as +1. Okay? So let me go ahead and write it out. Based on the priority list, H is assigned as +1. Once you assign 1, the leftover needs to be calculated. Now, if you have multiple unknowns, like 3 of them, you solve the first 2 from the table, you solve for the last one from math. Okay, pick the first, like, basically you leave the last one, you solve it with mathematically. So this is my last one here. So 2 and then +1 for the H here. So this is solved 1 here, answer. Plus whatever oxygen is going to add up to 0. So oxygen is going to be -2. Okay? So that's the example there. Now let's go to another example. H2O2. So now we have to do H and O. Let me zoom in a little bit. So again, we go through the list, right? So we have to write 2H plus 2O equals to 0. And then H was my priority. Remember, we just went through the list. H was my priority. I assign S plus 1. Now I have to calculate what oxygen is going to be. So 2 times +1 plus 2 of oxygen equals 0. 2 of oxygen equals -2. Each oxygen is -1. So the one that's not the highest priority, the last one, always changes depending on what compound you match with and what the other priority was.
And so this is just like this there's like a trick for this, right? Where you just like cross or like you go like you crisscross and then simplify. Or
No,
well, because like
this isn't the same thing as crisscrossing anymore.
oh, it's not.
You can still do it if you can see ions, but like I can show you like now. Here's one that you can't apply that. Okay, so that can work for some, but not always. So I like to make sure you just memorize the rules and calculate a leftover. So here's
Okay.
what you can't use. So like look at this one here, like C3H5O2 -1. And you have to find an oxidation state for all of them. Okay, so that one, like, I don't think you can use that trick anymore. So in this case here, you have to write out everybody here and equals to, it's going to add up to -1. So let's start there. So 3C plus 5H plus 2 oxygen equals to -1. Okay, and then we go through our priority list. So if we looked on the list, so remember you have carbon, hydrogen, oxygen. You got to see who comes first, right? So obviously it's not group 1, it's not group 2. So you have FHO, group 7, 6, and 5. So I always memorize group 1, group 2, FHO, group 7, 6, 5. Okay? And then I can see that H comes first and O comes next. And then carbon's not even on here. So carbon gets a leftover. Okay? So on my carbon here, we have to calculate that later. So let's go ahead and assign H as +1, +1. And we'll also assign O as -2. That's from the table of priority, okay? Now, once you do that, you have to calculate what carbon is, okay? So let's put it in here, 3C plus 5, +1, and then 2 of -2 equals to -1, and then you solve for what carbon is. So 3C, and then 5 minus 4, so it will be +1 here, equals to -1. 3C is actually -2. C is actually -2/3. So you come up with like super weird numbers for carbon usually because it's not even on a priority list. They always get the leftover. So that's one example for carbon. I want to do a few more carbons just to show you how carbon can vary a lot. Okay, so let's do CH4, a simple one first. Okay, so CH4 here, we have carbon and 4 hydrogen, that equals to 0. And from the list, it was group 1, group 2, FHO, group 7, 6, 5. H came first. So I'm going to go ahead and write, I know carbon plus 4 hydrogen equals to 0. And my H came as my first priority. Okay, and then obviously from there you can tell what carbon is going to be. So carbon is, I'm going to go ahead and write it out anyway, +1 equals to 0. Carbon equals to -4. You see how carbon always gets the leftover, and it's like -4, -2 or 3. It's just like all over the place. let's try another example with carbon. Let's do CO2, carbon dioxide. Okay, with carbon dioxide, you have one carbon and two oxygen, and that equals to 0. Who's my priority? Now again, the priority was group 1 metal, group 2 metal, F, H, O. So O came first, and then group 7, group 6, group 5. So O is my only one that shows up here. So O is -2. Okay, now because O is -2, carbon has to get the leftover. So carbon plus 2, -2 equals to 0. Carbon here is +4. Okay, so you just saw how carbon just can swing from -4 to +4. It can be -2 or 3. It's just all over the place. Another one here, CCl4. We can do just for fun. So CCl4 is carbon plus 4Cl equals to 0. So let's take a look at our priority list, okay, for this one. Group 1 metals, nope. Group 2 metals, nope. Because we're looking at CCl4. F, nope. H, nope. O, nope. Group 7, okay? Because group 7 is where you find chlorine. So you have to know chlorine is group 7, okay? And who's group 6 and group 5. So hopefully you guys remember that from the periodic table. So that's how we assign Cl here as -1 because it's group 7. And then based on that, you can calculate what carbon is. So carbon in this case is +4. So are we pretty okay with this? Okay, I'm gonna do some more polyatomic ions to show you examples. And then after we do this, we're actually gonna go into reactions. Okay, like full on reaction, because we're really doing just the basic blocks right now, just doing elements in a compound. And then later on give you a whole reaction, you do the oxidation state for every single element in the entire reaction. Okay, let's try some polyatomic ions here. This was 1, let's do another one. Actually, we'll do another 3. All right, I'm gonna go on. So I want you guys to try doing it. So this is review, but sometimes, you know, it's been a while, you don't remember, that's okay. We're doing a review because this is very important that you understand this part. Very, very important. It's nitrate, and we'll do ammonium also. So these are the 3 here for polyatomic ions. And then we can also do some compounds, F, Na2O2. We'll do ammonia also. So, yep, I think if we do this, we should be good. All right, so hopefully you've finished writing it. Let's go ahead and do one by one, and you can go ahead and work faster than I am too, that's fine. Just remember to, I'm just showing you how to do this. So S plus 4 oxygen equals to -2. And then you have to decide who's in your priority list. So you have sulfur and you have oxygen, okay? So based on the rules of this, I already kind of memorized it, but I'm gonna show you again. Group 1, group 2, F, H, O, right? Now, sulfur is in group 6, but it really appears after O anyway, so you go ahead and assign O and calculate sulfur. So O is -2. So we want to go ahead and calculate sulfur plus 4 of -2 equals to -2. Sulfur then is sulfur minus 8 equals to -2. So sulfur is +6. Okay, you can do nitrate also. Remember, N plus 3 oxygen equals to -1. And you have to decide who's on your priority list. So on your priority list, O comes first because N is in group 5. Group 5 comes below that, so oxygen takes priority, okay? So O is -2. And then we'll plug in -2 in there. So nitrogen is actually, so +5. All right, so let me know if you have questions, okay? Ideally, I want you guys to try doing this. Like, even if I'm showing you now, after the class today, I want you to write all these out again and see if you can remember how to do it. Like, can you still assign oxidation states? Okay, let's do some more. Nitrogen plus 4 hydrogen equals to +1. My hydrogen is my priority, is +1 according to my list. So I have to calculate what nitrogen is. So nitrogen is -3. All right. And then we want to do LIF. LIF is, pretty simple. So Li plus F equals to 0. Li is group 1, so Li is my first priority. And then F is calculated. So Li is +1 plus F equals to 0. So F is -1. Or if you knew the ions, Li is +1, F is the -1, you'd get the same answer. Then we have Na2O2. So this is another group 1 metal, right? So it's 2 sodium plus 2 oxygen equals to 0. Sodium is my priority, +1 because it's group 1. So you have to memorize the priorities, otherwise you calculate it wrong. 2 +1 plus 2 0 equals 2 oxygen equals 0. So 2 oxygen equals to -2. Oxygen equals to -1. And the last one here, nitrogen plus 3 hydrogen equals to 0. Hydrogen is my first priority. Hydrogen is +1. So we put nitrogen plus 3 +1 equals to 0. Nitrogen therefore is -3. So hopefully everyone's good. So here's an equation. CH4 plus 2O2 goes to CO2 plus 2H2O. Very simple combustion reaction. Okay, based on that, we actually assign all the oxidation states for all these guys already. I think we did. Did we do carbon dioxide? I think we did. Yeah, we did. We did water. We did oxygen. Well, oxygen is 0 anyway. No, we did CH4. So that's why we were practicing up here, so you can assign it for this reaction here. Okay, so I'm going to go ahead and from here tell you. So H for this guy is +1. C here is -4. If you don't remember how we got this, it's in the previous example on the previous page. O2, O is 0. Right here. CO2, O was my priority. And then I calculated carbon to be +4. Oops, not 14, 4. And then you have water. So another thing that students get confused with is, what do I do with this 2? Don't worry about it 2 at all. You are looking at the compound, not how many compounds there are. Just don't even worry about that, okay? So you have 2 hydrogen plus 1 oxygen equals to 0. The same thing that we just did earlier. So based on that, you'll do H is my priority plus 1, and O is -2. So that's what we were doing earlier. Now, when you put this together in an equation, you start seeing carbon has gone up from -4 to +4. You see that? So when it goes up in number, this is an oxidation process. Now, specifically, carbon in methane has been oxidized. Okay, do you see one that's going down in number? Who's going down in number? That one is being reduced. You guys see that? So H is not changing, right? But oxygen is going down from 0 to -2. So it goes down to this guy and that guy, and it's a reduction. Okay, now from Chem 1, they say the guy that's being oxidized is called the reducing agent. And then the guy that's being reduced is called the oxidizing agent. Now, the reason why we say that is because if CH4 was not there, the reduction will not happen. It's because CH4 was there, reduction is okay to take place. So this is an agent for reduction. So it's agent for the opposite process. Okay, so anything that's being oxidized will be the agent for reduction. Anything that's being reduced will be the agent for oxidizing. So that's where the name comes from. Fe plus MnO4 negative plus 4H plus turns to Fe3 plus MnO2 plus 2H2O. So what I want is for you guys to go ahead and assign oxidation states for every single one of these elements. And then we have to decide who's being reduced, who's being oxidized, who's the reducing agent, who's the oxidizing agent. So based on the rules that we learned, the first thing we want to look for is basically free element standing by itself will be 0. Do you see any free element standing by itself? So what's a free element standing by itself? It's just an element hanging out and there's no charge. That would be this guy. Okay, so Fe is the 0 right here. So hopefully everyone still remembers this. So 1 is done. And then we can go ahead and do the ions. The ions are easy. The ions really just have the oxidation state the same as the charge monatomic ions here. So H here is +1. And this Fe here is +3. Okay, and now we have to do this calculation, and this calculation. Well, we've done water before previously. Good morning. All right, so let's go ahead and do MnO4 negative. Okay, so it's 1 Mn plus 4 oxygen equals to -1. Now we have to decide who's your priority group. So who's your priority group, guys? Go through the list. Okay, the list was group 1, metal, group 2, metal, and an FHO, and then group 6, group 7, group 6, group 5. So O will come first, okay? And O is assigned as -2. So if O is -2, all we do is plug this -2 right there, and we'll calculate what Mn is going to be. So in this case here, Mn is going to be +7. All right. The next thing we want to do is take a look at this one here, MnO2. So in this case, Mn plus 2 oxygen equals to 0 because it's neutral charge. And then again, oxygen comes as my first priority, so I assign this as -2. And then I have to calculate what Mn is. So Mn would be Mn plus 2, -2 equals to 0. So each Mn would be +4. Okay, now we can do the same for water. We have H2O here. So you have 2H plus 1O equals to 0. Now you have to decide who's your priority. So group 1 metal, no. Group 2 metal, no. F, no. H. So H came first, okay? So H is assigned according to the priority rules, +1. So then we calculate what oxygen will be. Oxygen in this case will be 2 plus 1 plus oxygen equals to 0. Each oxygen is -2. Okay, so you guys will be working on this. Basically, every time you see a reaction, you should be able to tell the oxidation state of every single element in there. And then the next thing I want you to do is decide who's being oxidized and who's being reduced. Can you see who's being oxidized here? So what's the definition of oxidation? When the oxidation state numbers go up. If it goes up for the element, it's being oxidized. If it goes down for the element, it's being reduced. So very good. Iron here is going up. So this is an oxidation process. Now, the guy that's being oxidized, remember, we call it the reducing agent. Okay. And then let's try to see who is going to be reduced here. So do you see any element here that the number is coming down? So it's going to be Mn and MnO4 negative. So it's specifically manganese and permanganate ion is going to be reduced. So this is a reduction process. And right here, sometimes they'll ask you which element and which compound. That would be manganese in this compound here, this polyatomic ion. But typically you can just, sometimes they say this polyatomic ion here is the one that's called the...
There are a few things that we want to tell you about the FIDAR role distributions happening today. The first thing is that they can happen practically anywhere.
All right.
From the deserts to bustling cities around the world. Anyone, anywhere can use a little extra help. And also,
وأنا طبعا زي ما
Thanks for muting your mic. And you're supposed to be watching the video, this video anyway, so it might be very distracting for the whole entire class. So make sure you guys are all muted. All right, let's continue this. Okay, so let's go on to the next question here. Let's try another one. Try doing this on your own. So you can, I'll give you a little bit of time. It's I negative, Cr2O7, 2 negative, goes to Cr3 plus I2.
I have a quick question.
Yes?
So will it always just be like 2, like one is reducing and one is oxidizing? Because I see we also have the 4H and 2H2O. Do we just not do anything with that one?
Well, the numbers aren't changing.
Oh, okay. I get you.
If they're not changing, they're not participating in it. I mean, sometimes you'll see like see this previous example here, like this one goes to 2 parts and both of them were going down to -2. So it does happen. Sometimes there's 2 things in the reactant side that it's being oxidized or reduced, or sometimes it's one thing going to multiple things. That's possible. But your priority now is to be able to identify who's being oxidized and reduced. all the other pieces will fall into place usually.
Okay, thank you.
Multiple. You're welcome. So try this one here. So remember, try to assign who's 0 and then try to assign the ions. And then all you have is left one thing here that you have to calculate, okay? So in this case, can you tell me which one has a 0? Okay, so we're saying I negative being oxidized. So this guy here is a 0. This guy here is negative 1. This one here is positive 3. So your classmate is saying negative 1 going to 0. Yes, that one is being oxidized, okay? Oxidation or oxidize doesn't matter. This here is my reducing agent. All right, you do have to calculate this, okay? So you have 2Cr plus 7 oxygen equals to negative 2. And your priority in this case is oxygen. You just go through the list, group 1 metal, group 2 metal, F, H, and then O, okay? So very good. Chromium here is being reduced. So O here, since it was assigned as negative 2, you will be able to calculate chromium here. So each chromium, I'm trying to write all this stuff right now. So let me go over here. So 2 chromium is positive 12. Each chromium is positive 6. Okay, so chromium is going from 6 to 3. So yes, that one is being reduced. So this guy here is my oxidizing agent. Okay, so very good. Everyone seems to be getting this. So now what we want to do is actually learn to balance these redox reactions. I want to show you the slide that tells you the rules here. So let's see. Okay, it's gonna sound like a lot, but I'm gonna walk you through this. So slide 18 tells us how are we gonna balance these redox reactions. Okay, redox reactions are where in a reaction you can identify someone being oxidized and someone being reduced. Okay, number 1, it says step 1, assign oxidation state. So we just did that and we determined who's being oxidized and reduced. So we learned how to do step 1. The next step, it says write oxidation and reduction half reactions, including electrons. So we're gonna work on this. So basically, once you assign oxidation steps and you decide who's being oxidized and reduced, what we will do is split them. We'll split them into 2 halves. One side is oxidation, one side is reduction. And then we'll start balancing them. So there's a few steps here. Now, if it's acidic reaction, we stop at C. If it's a basic reaction, we go on all the way till D. So we will be doing acidic examples first, and then we'll do a basic example, knowing that basic is just one extra step in the balancing by mass. And then after you balance by the atom's mass, or atoms, you will balance it with charge by adding electrons in your equations, okay? So we'll do that. And then we'll make sure electron counts are good, and then we combine them back together. So there's a few steps, but I will walk you guys through it. And we'll start with the first, we'll do acidic examples first. We'll do ABC in there, and then we'll do a base one at the end, okay? All right, so let's go ahead and switch over. So I'll go ahead and write this is acidic. Under acidic conditions, okay? So when you see acidic, you should expect to have H plus and water because that's what makes it acidic. So here's my reaction. Fe2 plus MnO4 negative goes to Fe3 plus Mn2 plus. So go ahead and assign oxidation states there. And then I want you guys to, tell me who's being oxidized and who's being reduced. And then we'll work on balancing. So we're just doing step 1 right now, identifying all the oxidation states and who's being oxidized and who's being reduced. So we just did this one earlier, so you can take a look at that as well. Now, we do have a lot of ions. Can assign oxidation states of those ions the same as the charge. Okay, and if you look at the previous example, we determined that oxygen was my priority and manganese was +7 after you calculated it. Now, based on this, who's being oxidized? Okay. So you should be able to see iron is going from +2 to +3, so it is going up. This one's being oxidized, so we can say oxidation process here. So this guy is my reducing agent. And manganese here is being reduced. So this guy here would be my oxidizing agent. Okay, very good. All right, so once you determine this, we move on to the next step. We split them apart. So when you split them, I want you guys to leave some space, because we want to write out the explanation and stuff. So I'm gonna do oxidation here, and I'll skip a little bit space. We'll do reduction. We're gonna write 2 separate halves here, and leave space in between because we're gonna have to fill in the blanks with electrons and atoms. So I like to give it a little space, Fe2 plus. All I know is Fe2 plus is turning into Fe3 plus. That's all you write down from your determination here. And then the next one is MnO4 negative turns to Mn2 plus. So then I write it down here. Okay. Now, so we want to go through the steps to balance the atoms. Okay. So when you want to balance the atoms, it says, I'll show you the slide again, but I can recite it for you later too. Once you do it enough times, you start remembering. It says here, first, balance elements other than H and O. So that means elements that are non-H and non-O, we balance those first. And then after that, you see oxygen, you put water on the opposite side. And then after that, you see hydrogen, you put protons on the other side. That's where we will stop for acidic, okay? For basic, if you were to keep going, so these are put stuff on the opposite side. For basic, if you see protons, you put hydroxide, the same number on both sides. So that's the difference there for basic. Let's continue back over here. So what we see here is step 1, we need to balance non-H and non-O, which is iron. Do you agree that this is iron, one iron here and another iron here? The only thing different is the charge, but the masses are the same for the iron here. So in this case here, iron is already balanced, okay, atomic-wise. Now, after you balance the atoms, it says balance the charges by adding electrons. So that's the next step below it. I'll show you a step here. There's balance reaction by charge, by adjusting electrons. So how in the world do you want to adjust electrons? So what charges are electrons? Electrons are negative charge. So you want to make sure both sides have the same charge, okay? By adding electrons, which is a negative charge. You can only add electrons. You don't add protons, you don't add neutrons, you're adding electrons, okay? So if I have a charge of +2 over here, and I have a charge of +3 over here, how in the world am I going to make both sides the same charge if you can only add electrons? Electron will be bringing it down by 1. So that means you can only bring charges down so they match by adding electron to the side that's higher. So if this side is higher by 1 charge, I need 1 electron over here, which will be a -1 charge, and then a total here will be -2. So then both sides are now, not -2, +2, I can't count. So both sides are now +2. Okay? Very good. So we add it to the right side. So again, another indication of oxidation is electrons are on a product side. So you know you did it correctly. If you were doing oxidation, you somehow had an electron on this side, then you might have made a mistake somewhere. Okay, so that's an indication there. So once you do this step, we're done balancing the atoms and the charge. So we leave it alone for now because we then want to balance this guy down here. We balance the atoms and then we balance the charge, and then we try to combine these two lines together. So for the reduction here, we do the same thing. The first step is to balance the non-H and non-O. So I do see manganese that has to be balanced, non-H and non-O, right? So that's manganese, Mn here. Is it already balanced? Yes. There's 1 here, and there's 1 here. So I'll go ahead and write it out here, the steps, okay? So the first step here, since this one has a lot of steps, so it says balance non-H and non-O. We already did that because it's already balanced. Mn and Mn are balanced, okay? And say after that, okay, if you see O, put the same, or put amount of water on the opposite side to balance out the O, okay? I'll just put water. Put water on the opposite side. To balance it. We just need enough water's oxygen to balance the oxygen on the other side. Okay, so right now I'm going to rewrite this down here. So because it's the first example we're doing, I'm writing it really slowly out, step by step, with a lot of space in between. So we have MnO4 negative, and it's turning into Mn2 plus. We already knew the MnO was balanced. Now our job is to balance the oxygen. So you see 4 oxygen here? So that means I need 4 water on the other side. Why 4 water? Because each water has 1 oxygen, so you still have 4 oxygen, 4 oxygen. You just balance the O there. Right, the mass of the electron is really small, it doesn't change the mass. That's why they say focus on the mass of the atoms first, which is matching the atoms. And then we add in the charges because the electron is so light. So someone's saying we're adding 3 electrons. Actually, we're not there yet. You'll see that we don't actually add 3 electrons yet. Because you have to do all the other steps before. You actually have to go through the atom balancing before you can go to the charge part, okay? So you see how this is like balance reaction by mass. So we match the atoms, and then after you match the atoms, you match the charges. So you do have to walk through these steps first before you do the charge, okay? Yeah, that's okay. Yeah, we don't want to jump the gun on this one, right? Okay, so let's do this. So we have our 4 water. So then we did this part. So we check this. So the new thing I added was right here. Okay, I'm going to underline it so you see like this progression of us doing this. So from here, we go to that step. And then let's go to the third step. And the third step says, if you see H, put proton, H plus, on the opposite side to balance it. Okay, so now we have to balance the H from the water, basically. Now, how many H do you see on the water? So I'll rewrite it over here. MnO4 negative is going to Mn2 plus 4H2O. That's what we have so far. And we have to put H plus on the opposite side where you find hydrogen. So I do see 8 hydrogens here. Okay, so we see 8 hydrogens here. We want to go ahead and put 8 protons on the opposite side. Okay, so what I'm going to do is going to just write the 8 protons over here. So you see, that's why I say like leave space so you can like write, because sometimes you like end up writing a lot on the sides. So I'll go ahead, I'm going to underline this. This is what we did. We balanced the water by the H in there by adding protons on the opposite side. So now that we've done the steps A, B, and C for acidic, you see so how we did this A, B, and C here, and then since it's not basic, we will skip this step. We'll do this extra step for the basic reaction later. So we'll stop here. Our atoms are now officially balanced. So this atom-wise is balanced, but then now you have to look at the charge. So I like to write down the next step after this is balance the charge. How do we balance charge? By adding electrons to higher charge side. So we just have to bring the charge down. So we add electrons to the higher charge side. Okay. So let's go ahead. I'm going to rewrite this whole equation down here so we can look at the charges. 8H plus MnO4 negative turns to Mn2 plus 4 water. And then in this case here, so I have 8 protons that each one is plus 1, but I have 8 of them. So this is 8 plus, and this is 1 polyatomic ion is -1. So 8 positive and 1 negative charge. Well, this is a really bad breath. I don't know what's up with me. Let's try that again. This here is 8 plus and -1, so this is +7 on this side. Okay, now I see a +2, and water has no charge. So overall, it's still +2 over here. So we have 7 and 2, and we want to add electrons to the higher charge side so we can bring it down to match the lower side. How many electrons do we need here? From 7 to go down to 2, we actually need 5 electrons. So I'll go ahead and underline this one. So the new step I'm underlining, okay? So now, after you do that, this line is now balanced by charge and by atoms. And that line up here is also balanced by charge and atom, but that one's a lot shorter because it didn't have H and O to balance. So we were done right away with that. So we take these two and we want to combine them, okay? Now to combine them, so now combine both halves, so both oxidation and reduction reactions. After we match the electron count. So your electrons have to be the same count, okay? You can't just put in like, see like how this one is 1 electron and that one's 5? It's not gonna be a full circle. One has to give up 5 for the other one to receive 5. So how do you make this one turn to 5? So all you do is you take this guy and you multiply it by 5. Okay, so that's why we have to multiply by 5 because we're trying to match 5 electrons. So what I'm going to do is once I multiply by 5, I'm going to rewrite it down here, okay? So now it's oxidation half is 5Fe2 plus goes to 5Fe3 plus 5 electron. And then my reduction half is going to be 5E plus 8H plus MnO4 negative goes to Mn2 plus 4H2O. Now we're talking. Because you're matched. Okay, you have to make sure electrons match there. And later on, when you're doing Nernst's equation, you'll see this number of electrons here is actually put into your equation anyway. But we're not doing that right now. We're just balancing. So let's go up. Once we balance this is good. So that crosses off. Now these are all on my reactant side. These are all on my product side. Then you cross off the electron because they canceled. Then we can start writing the complete balance equation. So balance redox is basically writing all of those guys out. So it's 5Fe2 plus 8H plus MnO4 negative goes to 5Fe3 plus Mn2 plus 4 water. So that's how we would do it. Okay, so it's not hard. It's just a lot of steps to remember. If you practice, it will get easier. Okay? So this is under balance, under acidic condition. So the next thing we want to do is we'll try this again because it's kind of like learning a new language here. So we do definitely want to practice. So we will practice. Let's see. All right, yeah, we'll be doing some practice in here. All right, let's try this next question. So I'm gonna go ahead and turn the page. And we'll try to balance this out. Now this time I'm not gonna write every single step out. We're just gonna leave some space and fill in the blanks, okay? So again, we're still doing another acidic one to get familiar with it. The question is I negative plus Cr2O7 2 minus goes to Cr3 plus I2. So we just did that equation earlier just to practice like finding who's oxidizing and who's reducing. So hopefully you still remember that. I'm gonna go ahead and fill in the oxidation states. Hopefully you still remember it. We just did this one like earlier. Okay, I'll show you. This is like on the previous page, right on the bottom over here. Okay. So I just rewrote those states here. Then we have to decide who's being oxidized, who's being reduced. So in this case here, we have I negative to I2. That number is going up, so that's oxidation. This one is being reduced. So I get to separate them. Okay, so I'm going to write oxidation line right here. And we'll do a reduction line a little bit below it. Oxidation is I negative goes to I2. Reduction is Cr2O7 2 minus goes to Cr3 plus. Okay, so now we want to go through the motion and balance these reactions. Number one, we'll do each half separately. We'll do balance the atom and then balance the charge for oxidation. Then we'll do balance the atoms and then balance the charge for reduction. And then we combine them together. When we combine, we have to make sure the electron counts are the same. Okay? All right. So the rule is balance non-H and non-O first. So that would mean iodine here has to be balanced. So I, there's one I, and there's two I's here. How in the world are you going to balance it? You put a 2 next to it. Okay? So well, now both sides have 2, so that's good. And then you don't see H, you don't see O, right? You don't see oxygen to put water, you don't see hydrogen to put protons, you don't have any of it. So the atoms are officially balanced. So the next thing is, once the atoms are balanced, we want to go ahead and balance the charge. So on this side here, my charge is -2. This side here is 0. So I have to add in electrons to the higher charge side to make sure both sides are the same. So do you guys agree we add electrons to the product side on the right side here? And we actually have to add 2 electrons. So this is -2, 0 and -2 adds up to -2. Okay, so that side is done, balanced for now, atoms and charges. Now we move to the reduction side. Okay, so the reduction side, we follow the same rules. Number 1, balance non-H and non-O. So that would mean balance the CR. So I have 2 CR and I have 1 CR on the product side, 2 on the reactant side, 1 on the product. So how are we going to balance it? All you have to do in this case is we actually just put a 2 in front of this guy. Okay? So once we do that, our chromium is balanced. Then we focus on the next step. The next step says, if you see oxygen, put water on the opposite side to balance it. Right, so we add 7 water to the opposite side, so to the product side. So we just balance the oxygen. Now, the next step says, if you see hydrogen, add protons on the opposite side to balance it. So we're still doing opposite, remember? So how many protons do you see? How many protons do we have to add? Because we have 14 hydrogen here. So you actually need 14 protons on the opposite side. Okay? Very good. 14 protons, so make sure you put the H plus, okay? So the thing says balance non-H, non-O, and then the next step was if you see oxygen, put in water, and then the next step was if you see hydrogen, put in protons. So that was the end of acidic atomic balancing. So we stop right there. So the balanced atoms here are as shown. So we do have 2 chromium, we do have 7 oxygen, and you have 14 hydrogen. So it does match already. So our job after this is once you balance the atom, you have to balance the charges. Okay, so let's take a look at the charges here. I have 14 positive 1, so it's 14 positive 1. And then this is -2. So overall is positive 14 and then -2, I get positive 12 on this side. And then on this side here, water is neutral, so 0 charge, and then you have 2, 3 plus here. So that means it's positive 6 charge on the product side. Everyone agree on the charges? I usually lose a few people with the charge part. So hopefully I'm explaining it clear enough. So all I'm doing is taking, well, there's 2 here, and there's only 1 mole, and there's 1 plus, but there's 14. So altogether I have 14 and -2, I have plus 12. And then this is neutral, so 7 times 0 plus 2 times 3 is positive 6. Now, because I have 2 sides different charges, how many electrons should I add to which side to make sure the charges are now the same? So you do see there's a difference of 6, right? We have to add 6 to the left side, which is to the reactant side. 6 electrons right here. So another good thing to remember is oxidation is the loss of electrons. So electron comes out as a product. Reduction is the gain of electron. Electron will be on the reactant side. So just little things to remember to help you check your work. Because if you do accidentally put the 6 right there, you would have been like, wait, there's product and here's product, so something's wrong. So you can always double check yourself that way. So This here is -6. Now I have a grand total of -6 on both sides. Not -6, +6. Okay, so now both sides are the same. Now, the next step would be to combine them too. So combine these two steps, but we can't combine if the electron counts are different. So this one has 6 electrons, this one has 2 electrons. How can we make both sides the same? Well, easiest thing to do is just take this guy and times 3, okay? And then that would give it 6 electrons, and then we just have to rewrite this. So I'm going to rewrite the oxidation on the bottom here after it's multiplied by 3. Okay, it's going to be 6I negative goes to 3I2 plus 6 electrons. And then we can combine it with this. So I'll just write a reduction right underneath it so it will be easier to see. You don't have to rewrite it. I'm just writing it to be easier to combine. All right, so these are all my reactants. These are all my products. And obviously I know the electrons cancel off, so I don't have to write that. And then I can write the total of everybody all balanced, okay? So this is balanced in acidic condition. There's 6I negative plus Cr2O7 2 minus plus 14H plus equals to 3I2 plus 2Cr3 plus 7 water. So the questions you will see more on a quiz, on a test, is they won't ask you, well, they usually don't ask you to write the whole equation out because it's going to be multiple choice. So a lot of times they ask you, what is the total of all the coefficients in this reaction after it's balanced? Well, then you have to add all the coefficients of 6 plus 1 plus 14 plus 3 plus 2 plus 7. Sometimes I ask you, what's the coefficient in front of Cr3 plus? Then you'll be saying 2. What's the coefficient in front of water? 7. No, they'll ask you stuff like that. But as long as you have the balanced equation, you will be able to answer those multiple choice questions. Okay? So that was one acidic problem. Let's try one more just to make sure we are really good with this. I'm going to go ahead and turn it to the next page. And then after that, I think we have enough acidic examples. We can probably do a basic one. So another acidic. So this one is zinc 2 plus ammonium NH4 positive goes to zinc solid, just zinc 0 charge, plus NO3 -1 charge nitrate. So go ahead and assign all the states. And then decide who's being oxidized, who's being reduced. We did these examples last week also. So now I have the oxidation states written out. Hopefully you got the same answers, and I actually showed you how to do these last week, pretty sure it was on the list. Yep, we did that together. Okay. Tell me who's being oxidized and who's being reduced. So zinc is going down, nitrogen is going up. So nitrogen is being oxidized, zinc is being reduced. Very good. So let's go ahead and write it out. Oh, I kind of read a little too high there. Let me bring it down a little bit. Do oxidation on this line here. Oxidation was NH4 plus turns to NO3 negative 1. Okay. And then we'll do the reduction. It was zinc 2 plus to zinc. Okay. Let's go ahead and balance the atoms on the top one first, oxidation. So balance non-H and non-O. So that means balance the nitrogen. It's already good. 1 here and 1 here. So the next step, it says, if you see oxygen, put water on the opposite side. Okay, do you see oxygen in there? Well, I see 3 oxygens. So that means I put 3 waters on the opposite side. Okay, now the next thing it says, if you see hydrogen, put protons on the opposite side. So how many protons should we be putting in? I see 4 hydrogen plus, and then in this case, 6 hydrogen. So I actually see 10 hydrogens here. 1, 2, 3, 4, and then here's 6. Okay, so I have to add 10 protons on the opposite side. Everyone still following? Okay, so the rule was balance non-H and non-O. And then the next one is if you see oxygen, put water on the opposite side. And the next one was if you see hydrogen, put protons on the opposite side. We just did those 3 steps for acidic. So we stopped there for our atoms balancing. We already balanced all the atoms. And the next thing we want to do is balance the charge. Okay, so balance charge, I can see this side is +1 because that's neutral and that's +1. And then this side here is a lot bigger because this is 10 minus 1, so this is +9. All right, so this side's a lot bigger because it's 10, +1, and -1, so 9. So you have to add how many electrons to which side? So looks like you add electrons to the high charge side so we can bring it down. And to bring 9 down to 1, you actually have to add 8 electrons. So I'm going to go ahead and write -8 here, and then say the grand total will be +1 on both sides. So we just balanced the atoms and the charges for oxidation. Very good. So the next thing we want to do is do the same for the reduction line. And reduction here is the easy one because there's nothing else, no H, no O, none of that, just zinc. So zinc is good, right? It's already balanced. You guys see that? And then there's no oxygen, there's no water to add, and there's no hydrogen, so there's no protons to add, so we can skip all of that. So zinc is already balanced, that's good. Now we want to just balance the charge. So this side here is +2, this side here is 0. So I have to add 2 electrons to the reactant side, plus -2. So my grand total on this side is also 0. So I have both sides balanced. Oxidation is balanced by atoms and charge. Reduction is balanced by atoms and charge. And now our job is to combine them. Can you combine as is? We cannot combine until our electron counts are the same. It has to make a full circle. So if this one has 8, this one has 2, you have to take the 2, this line, and times 4. Okay, so I'm going to go rewrite it here. Reduction of 3 times 4. It's going to give me 4 zinc plus 8 electrons, 4 zinc. And then I'll rewrite the oxidation right by it so I can compare. NH4 positive plus 3 water turns to NO3 negative plus 10 H plus 8 electrons. So all my reactants, all my products. I can cross out my electrons because they match. So my balance is going to be 4 zinc 2 plus NH4 positive plus 3 water going to 4 zinc plus NO3 negative plus 10 H plus. So this is under acidic conditions. Okay. So next one, let's do a basic one. Remember, basic is literally all the same steps, except during a balanced atom, we add one extra step. Okay, so let me tell you what the extra step was again. It was simply, if you have base, if you see H plus, you put in hydroxide on both sides because H and OH will make water. Okay, I'll write it out when we do it together. So let's see. I think I can squeeze it in here. Yeah, I can. So let's do a basic one. I negative plus MnO4 negative goes to I2 plus MnO2. Okay, so let's go ahead and assign all the oxidation states here. We did this one earlier, we did the ones earlier too, so hopefully you still remember that. So once you have that, all right, so the challenge for students here is, first of all, when you see the balance reader, you're like, you know, I don't even remember how to do oxidation states, so you can't even start this question. And that's why we went through so much review to teach you how to do the oxidation states first, okay? So once you get the oxidation states, we'll split them to the half where oxidation and reduction. So you can clearly see manganese is being reduced. Iodine here is being oxidized. Okay, so I'll go ahead and write it out. OX is I negative turning into I2. The reduction line is MnO4 turning into MnO2. Okay, I like to leave a little space because you're probably gonna have to add stuff in here. Hopefully there's enough space there. Probably not. If there's not enough space, I'll just write on the bottom here on the reactant side, okay? Let's go ahead and do the balancing now. I negative and I2, so we have to balance just the I, so all you do is put a 2 in front of this guy. So that one's atom balance. Now you have to balance the charge. This is -2, this is 0. So you add a 2 electron here. So both sides is now -2. So that one's done. Okay, let me know if you guys have questions. Now we want to go ahead and do this guy here. So this one here, you start seeing, oh, look, there's oxygens here. So you have to do the oxygen and the hydrogen and the protons, those kind of stuff. So let's balance the non-H and non-O, Mn and Mn, that's good. And then it says, if you see oxygen, put water on the opposite side. Okay, how many oxygens do you see? Well, I see 4 on this side and I see 2 on this side. So this side, I'm short because now I have, this is 2, that's 4. I actually have 2 extra over here. So I need to balance on the opposite side where I need to put 2 waters. Agree? Because I have 4, now I have 4. Because it's 2O and 2O. So that's how it's balanced. Okay, we add water to the opposite side of extra so you can balance it out. So now that we do that, in the next step it says, if you see hydrogen, put protons on the opposite side. Do you see hydrogen? Yeah, I see it. I have 4. So I'm going to put protons on the opposite side, so 4H+. Now, normally this is where we would stop. If it was acidic, we would just stop right here and we'll balance the charges. But this one's basic, so we have a 1 extra step this time. Okay, so what's the extra step? I'll write it out. The extra step is if you see H+, add OH- on both sides. Okay, and then you have to remember H+ plus OH- turns to H2O. So I see 4 protons, so I have to put 4 hydroxides on this side, and I have to put 4 hydroxides on the opposite side. It says on both sides. Okay, that's how you can turn something acidic into basic, because you're turning this into water and you're turning this to hydroxide. So now you can see there's 4 waters here. Okay, so I'm going to go ahead and rewrite this on the bottom because you also notice there's 4 water and there's 2 water here. Do you notice I can go ahead and cancel that off, right? So this 2 water and that's 4 water. So I can totally cancel this off and just cancel this and turn it into 2 right there. So I'm going to rewrite it. So now what I have is Mn, so reduction still, MnO4 negative plus 2 water. And then you get MnO2 plus 4OH. See, now it looks like it's in a basic condition because there's water and there's hydroxide. So the next thing we do is the atoms are all balanced now. Yes, the question will have to say if it's acidic or basic, otherwise you won't know what to do. So they'll say under acidic conditions, balance this redox, or they'll say under basic conditions, balance this redox. So they'll give it to you. Because basic and acidic will lead to 2 different answers. Okay? All right, so we have this here. This is for basic atoms. You have water and your hydroxide. And all these guys are balanced out atomic wise. So now all we have to focus on is just balance the charges. Okay? So that's neutral, that's 0, that's -1. So on this side I have -1 here. On this side here, I have 4 negative, and that's neutral, so this is -4. So I have -1 and -4. How am I going to make both sides the same? I have to add electrons to the higher charge. So that means add 3 electrons to the reactant side. So both sides will be -4. Okay? So now that we have that, we actually balance the atoms and the charge. So we have these 2 halves that we want to combine together. Can we combine as is? It doesn't match the electron count, does it? This one has 2, this one has 3, so we can't combine it yet. So we have to take this guy and times 3, this guy and times 2, so both of them will end up being 6 electrons. So let me rewrite it out. So oxidation is times 3. Reduction was times 2. So this will be 6I going to 3I2 plus 6 electrons. And then I do this one, 2MnO4 plus 4H2O plus 6 electrons going to 2MnO2 plus 8 hydroxides. Then we can combine them. This is on my reactant side. This is my product side. Cross of the electrons. Okay, so let's go ahead and write it out. Total balance. So I'm going to write all in this since I'm running out of space. So the balance is going to be, it's going to like be a little bit of a, I have to write in 2 lines, okay? So it's 6I, 2MnO4 for water. And then equals to 3I2 plus 2MnO2 plus 8 hydroxide. That would be the balance one under basic condition. So they'll definitely tell you in a question if it's acidic or basic. Otherwise, like you can't really solve it. Okay? So that's the first part of our chapter, learning how to balance redox reactions. So you just have to practice that and get, pretty familiar with it. And then we want to move on to the next part. We want to talk about voltaic or galvanic cells a little bit and learn how to look at the tables, which you kind of did for your lab already. So that's kind of nice. So everyone good with this? I'm going to go ahead and show you some slides. So we are going to look at slide number 30 here. So basically, voltaic cells or galvanic cells is the same, it's just a different name, same cell. These are spontaneous cells. So spontaneous meaning once you put it together, it'll automatically start going, like it will generate electricity because it's just spontaneously going to happen, okay? So how can you measure the current is by, like imagining this is the river current. Now, when you have a big current, there's a lot of water flowing through quickly, right? So the same idea for electrons. If you have a lot of electrons flowing through, it says here, the current is a monoelectric charge that passes a point at a given period of time. So it's kind of like the river here. If it's like, flowing a lot faster, a lot of electrons passing through, then you have a higher current. Okay, and it always goes from the high point to the low point. So we'll talk about those potentials as well. So chemical reactions. So if you were to put this, so this is a piece of zinc metal, it should be shining silver, and you put it into a copper 2 sulfate solution. So copper 2 sulfate, the color is blue because of copper 2 ion. So there's copper 2 ions floating in here, and there's zinc solid. And spontaneously, this reaction will turn into this, where the blue fades because the copper 2 plus ions is turning into copper and depositing on the zinc. It looks kind of black here, but it's really the copper part, okay? The copper atom is depositing itself on the zinc. And at the same time, because this is a redox, the zinc is actually being oxidized from zinc metal to zinc ion. So you actually see, let's zoom in a little bit so you can see the slide. See, I don't know if you can see it. It says this is zinc 2 plus ion. So the metal is releasing the ion out, and copper ion here is going to turn itself into copper atom and deposit onto the metal. So the overall reaction is zinc solid plus copper 2 ion is turning into zinc 2 plus ion and copper solid. Okay, this is a redox reaction. So So when you see this happens, you stick it in there, automatically it happens. You don't have to do anything. It's just, it has to meet and it'll happen. So this is why they call it a spontaneous reaction. Now, obviously we notice there's a redox happening. If you were able to separate these into two separate containers and connect them using a wire, you can make the electrons flow through the wire and generate electricity spontaneously. And this is the concept of having a battery. All batteries are voltaic cells because they're using chemicals, and then as soon as you hook it up, it spontaneously happens and it generates a flow of electron. Okay, so what you do to split this apart, so we have a system of zinc and copper. You want to split it into two separate beakers and connect it using electrical wire here. So you have one beaker is going to be filled with zinc. One beaker will be filled with copper stuff. So you need to have both components. You need to have a solid, so solid zinc, solid copper, because we're talking zinc and copper, and you have to have the aqueous form, the zinc ion, and you have the aqueous form copper ion. So these are copper 2+ ion, zinc 2+ ion floating around. And you separate them like that. As soon as you clip them on, the circuit is complete, it starts flowing. The electron just automatically flows and the light bulb will turn on. Okay, so that's because we know how to force, we know this is a spontaneous reaction, and if you force the electron to travel to complete the circuit, you can actually harvest the electricity right there. Okay, so this is a voltaic cell or galvanic cell. Now, main parts here that we want to identify is when you have a voltaic cell, you will have to have electrodes on both sides. So these electrodes here must be solid contact points and preferably something that you use in a reaction. If your reaction doesn't have a metal solid that you can use, then you will you just use a inert solid metal contact point, and that would be platinum solid. Okay, but if you have your, if you can find zinc solid, and zinc is in your reaction anyway, go ahead and get a piece of zinc. And then you have copper solid. Well, copper solid is part of reaction, use copper solid. So these here are your solid electrode contact points here, and you generally use the solid that's in your reaction. If you don't have a solid in your reaction, you will use platinum solid, okay? Now, we also notice that because we know the zinc solid on the picture above, that it spontaneously turns into zinc ion. Zinc here is being oxidized and copper ion is turning into copper solid. Copper is being reduced. So the side that is being oxidized has the anode electrode. Okay, so zinc here, zinc solid is your anode electrode because that's where oxidation happens. So oxidation happens at anode, reduction happens where cathode is. So cathode is associated with the reduction, anode is associated with oxidation. Okay, and these are the solid electrodes here. Now you want to connect them using a wire. Now, and also because zinc is being oxidized, oxidation is the loss of electrons. Electrons are going to flow from anode side towards cathode side, because cathode is receiving the 2 electrons. And this is why we have to be so picky about having the electron counts match, because this one has to give out 2 in order for this side to receive 2. That's how you make a full circle, okay? So that's part of it. So we talked about the electrodes. We talked about connecting it. And so because the electrons are coming up from the oxidation side, electrons coming off towards here, we actually label the anode as negative because electron and negative are repulsion. So it'll leave the negative charge and it'll go towards the positive sign. So cathode is associated with a plus sign here for voltaic cells. Okay, so again, gotta remember, we have electrodes. We have anode on the oxidation side. Anode is labeled as negative. Cathode is labeled as positive. You also know the direction is from anode towards cathode where the electrons are flowing. Okay, so that's another thing. Now, there's an extra thing here right in the middle. This is called a salt bridge. Salt bridge are ions, so they're basically usually like ions that are spectator ions in this case. So take a look at the spectator ion here. You have zinc and nitrate. Nitrate is my spectator ion, copper, nitrate is my spectator ion. So a lot of times you have to use, well, obviously you have to use a soluble something because otherwise it won't be in a solution. So we can use like sodium nitrate or potassium nitrate because, you know, nitrate was already the spectator ion here. You can use nitrate. So anything that's soluble to help you balance the charges. Okay, so in this case here, in this bridge here, they put a solution of potassium nitrate because it has spectator ions. So what's the function of your salt bridge? The salt bridge works to balance out charges. So over time, electrons are going in negative charge. So over time, this is getting more and more negative. And it's not going to be balanced. So you have to have a positive charge flowing in from the salt bridge to help balance it out. So wherever electrons are going, it's going to build up a negative charge. So you need a positive ion from the salt bridge to balance that. And this electron is leaving here, is losing the negative charge here. So you need the negative charge to come in here to balance out the charges. So salt bridge function is to balance out charges. Okay. So, so basically that's the setup of our galvanic cell. So there's components, there's electrodes, there's electrolytes, and they're two separate things. So if you have zinc 2 plus and zinc, so this is zinc 2 plus solution, zinc solid, copper 2 plus solution, copper solid, connect it using a wire, and it goes from anode to cathode. Anode is negative sign, cathode is positive sign, and the salt bridge provides the ions to balance out the charges. So wherever the electron is coming in, the positive charge has to balance it. Electrons are leaving, negative ion goes in to balance the charge. So that's one way to describe this whole cell here. Now, a lot of times, sometimes I either draw it out or I write a chemical equation. So this here can be represented by these two half cells, or I could have just written this chemical reaction right there. There's another way to explain this diagram here. Okay, so that's what we call electrochemical cell notation. So instead of drawing out a picture, I can actually describe this cell using a cell notation. So let me show you what cell notation means. So you can read through the slides. It explains the components that I just talked about: salt bridge, electrodes, and half cells. We talked about all of that, right? Okay. So how like the labeling is negative and the labeling is positive here. It talks about that. So just make sure you go over the slides here. I just explained it basically. You do want to remember the current is the flow of electrons. So amps is the unit for current, and amps is also coulombs per second. Okay, so that's something it'll be useful at the end of this chapter. So keep that in mind. Amps is coulombs per second, right there. And then you'll have voltage. Voltage is joules per coulombs. Okay. You'll see the voltage table shortly. So let's go ahead and show you the cell notation. Okay, so we're going to talk about the cell notation. So what you do is you write the anode first, which is the solid part. And then every time you have a different phase, you draw a single line. Okay, if it's the same phase, you use a comma in between. So you have to write the anode, draw a line because that's the only solid, and then you write the electrolyte, and then you draw a double line signifying going to the next beaker. That's basically the salt bridge sign. And then you write electrolytes, and then you do a single line and you write the cathode. Okay, so let's try it for this picture here that we just talked about, right? We talked about it. So we said the half oxidation was zinc to zinc 2 plus, the reduction was Cu 2 plus to Cu. And then we said we can write an overall equation using this that was on the other side, right? It's zinc solid plus copper 2 plus, that's my reactant, and then zinc 2 plus and copper solid, that's my product. So that's all in here. Now, if you were to write it in an electrochemical cell notation, this is what it looks like. Write the anode first, so zinc solid, draw a line. You don't write the spectator ions, you just write whoever is changing actually, right? So the nitrates here don't count, the potassium don't count, they're all spectator ions. So you write zinc solid and then zinc 2 plus ions in here. So you have to write the phases because otherwise then you need to know it's different phase. So that's why you draw a solid line. So zinc solid, solid line, zinc 2 plus, aqueous, and then this stuff is done. We'll draw a salt bridge, go to the next beaker. And then at the end here, you put the cathode, which is copper solid, and you also list out the electrolytes, which is Cu2 plus here. So that's how we would do electrochemical cell notations. Okay, so we're at slide 41 on our chapter here, and I'm going to show you, like, we talked about voltage, right? So the difference in potential is between anode and cathode is a cell potential, and we measure this. We'll have a table full of cell potentials in voltage. Okay, so you'll have E standard cells because in standard case, the table will show you values for standard conditions, which is 25 Celsius, 1 atm for gas, and 1 molarity for solutions. This is the anode, that's the cathode, and then these are the electrolytes in it, and you separate different phases with a single line. Same phase, you use a comma. If it's finished in one beaker, the next beaker, before you start the next beaker, you draw the salt bridge, which is 2 lines, okay? So we mentioned using inert electrodes here. Inert electrodes that we will use, what we will end up using is platinum. So I want to show you this example here. I've got to zoom in a little bit. This is on slide number 43. So take a look at this picture here. And if you look at the oxidation reaction, there's the iron solid going to iron 2 plus. Okay, and then on there, so there's a solid here for oxidation, so there's no problem, you can use this as anode. But if you take a look at the reduction beaker, these are all ions. So aqueous ion, and an electron, and an ion, that's aqueous, and then aqueous ion, and then there's liquid. So basically, there's no solid in here. So when there's no solid, you see what they end up using? They use platinum as your cathode in this case here. Because whenever you don't have a solid, you have to use a solid still, so you use platinum, it's inert. So our electrochemical notation here for the first beaker is platinum here. I mean, not platinum, iron. So platinum goes on the side. You see how this is inert goes here, and then this is the regular one. The only time you use platinum is when you don't have a solid in your equation in here like that. And obviously you can't see any solids in here as well. So see here, single line, and in this beaker there's Fe, and then to the next beaker we draw a double line, and then you write all your aqueous stuff down. You don't have to worry about the water liquid in this case. So MnO4, AQ, and then you notice this is AQ, this is aqueous also. So they put a comma in between these guys because they're the same phase. When they're different phases, that's when you use a single solid line through, okay? And then you separate it and you get platinum in this case, okay? So that's an example of how we would write electrochemical cell notation. Why don't we practice an example real quick, okay? So let's go ahead and start that. So here's a question. I'm going to zoom out a little bit first. All right, the question I have is 3Cl2 gas plus 2Fe solid turns to 6Cl negative aqueous plus 2Fe3 plus aqueous. So in this case here, you have to assign oxidation states so you can tell who's being oxidized and who's being reduced. They want you to take this. So from this chemical reaction, tell me who's being oxidized and who's being reduced, and then write a electrochemical cell notation. We're going to find out who's being oxidized, who's being reduced, and then we'll write the chemical cell notation. So hopefully you guys still remember all the oxidation states here. Can you try assigning them real quick? So for this case here, hopefully we remember this is 0 here. Fe is also 0, okay? And then this is -1, and this is +3. So you can see Fe was being oxidized, and chlorine here was being reduced. Okay, so we can say oxidized is Fe going to Fe3 plus. Reduce is Cl2 gas going to Cl negative. Okay, so in this case here, I have a solid on my oxidation side, but I don't have a solid on my reduction side. So who am I going to use for my cathode? I have to use platinum for this guy. Okay, so that's an example. So if I were to write my electrochemical cell notation, I would use anode. So anode is this guy. Okay, and then what else should be on that side? It should be Fe3 plus. Okay, and that's all on this side here because it's iron and iron 3 plus. And then you do the salt bridge and you cross over to the other side. So what are the two things in there on the other side? So there'll be chlorine gas and there'll be chloride ion. So they're two different phases, so you have to separate them. Okay, so that's that, but we don't have a solid for the cathode, so we have to add platinum. Okay, so hopefully everyone's following. So you can actually go from a chemical reaction and then you can write the cell notation out. And from there, you can also find who's being oxidized, who's being reduced. And of course, you could have drawn the picture out, but the picture is going to look something like what all the others we've seen. And we'll be drawing some out in pictures in a little bit anyway, okay? All right, so if you had a picture, this would be this side is exactly the same as iron, but this is iron 3 solution in here. And then you'll have cathode electrode here of platinum. And then instead of these other guys in here, you'll have chloride aqueous and chlorine gas coming out. So you'll see bubbles as well. All right, so let's talk about our potentials here. We talked about how the river, the water flows from high point to a low point. So the same idea here, electrons will actually flow where you have high potential going to low potential, okay? So what we want to do is, we can measure the difference in potential of two separate beakers, but we actually don't know each number separately. At first, if you have two parts, you can know the difference between these two. So for them to build a table, what they did was to say, well, let's assign one of these guys as 0. And then when everybody compared to it, the number will be in reference to this 0 number, okay? So this 0 here, the one that's set as 0 is the standard hydrogen electrode. You have platinum here as your inert electrode here, and then you have hydrogen gas and hydrogen ion, and they're going to be standard conditions, so it's 1 atm and 1 molarity. So they're watching actually the standard half reaction on the reduction table. We're looking at reduction of H plus to hydrogen gas. Okay, and this guy is 0. Okay, now then they put everybody relative to this guy. So this is the one side, and then the other side they'll put another beaker, and they hook it up, and they'll see, okay, if this is 0, the number that I get from this reading here, the difference is the number that goes on the table. Okay, so let's take a look at how it's going to look like. So here's an example. The example here is, so this is my standard cell. This is a 0. Okay, so it's hydrogen ion and hydrogen gas. That's the reduction here. And then we have platinum solid here because they don't have solid, so they put platinum here. And notice they wrote, if it's a concentration solution, they always like to write 1 molarity. 1 molarity is standard condition. So in this case here, they hooked it up and they saw the number as 0.76. If this one is 0, that means that one's 0.76. Okay, now what does the 0.76 mean? So that goes into the table. Okay, so and that number here, it says 0.76. So let's take a look at the table and see where zinc is. Okay, now this is an oxidation though. Okay, so let me show you the table. The table is pretty long. You don't have to memorize it. So here's the table here, and here's another one. And you'll notice zinc here is negative 0.76 on the table. So you're like, why? Why is it negative? The picture showed me positive. Well, in the picture, it's because you were getting a positive 0.76 because zinc was being oxidized. Okay, so notice that this table here is for only reduction values. So all these are reduction equations. If you take a look, they're all reduction equations, okay? The electrons are only on the reactant side. So they're saying, if I give you the reduction table, you can find the oxidation numbers because it's the opposite side. So they basically found out that zinc oxidation was positive 0.76 compared to 0. So the reduction must be negative 0.06. Okay, so remember, oxidation and reduction, literally same number, opposite signs. Okay, now if you had to write positive 0.76, how would you do it? You would write zinc turning into zinc 2 plus 2 electrons, and the E oxidation is positive 0.76. You just kind of flip the reaction around, flip the sign around. Okay, so let me explain this table here a little bit. So we were talking about a table, it came from referring to comparing everyone to this line here that's 0. So hydrogen ion turning to hydrogen gas is set as 0, 1 molarity, 1 atm. Now everybody above it has a positive number. Notice that? Okay. So from most positive down to 0, and then from 0 to most negative, really, really negative. So what does this positive, more negative number mean? The more positive the value for reduction here, it likes to be reduced even more. The more positive the reduction value, standard E, not reduction is, it's gonna love to be reduced. So that means F2 loves to reduce to F negative. That's common knowledge because we know fluorine loves electrons. Every time fluorine sees an electron, fluorine's going to get the electron because it's super electronegative. So that's why fluorine here has the biggest number in its table because it really loves to be reduced. It loves to reduce itself. So who's being reduced? F2 is being reduced to F negative. And because it loves to be reduced compared to hydrogen or compared to anyone below it, everybody else will have to say, okay, you win. If you reduce, I must oxidize. Everybody below this has to be oxidized if paired with F2. Okay, so you're starting to see that the top here loves to be reduced the most. Now, if you keep going down, they're like, okay, I still like to be reduced, but it's getting less and less and less, right? And it goes all the way to 0. 0 is kind of like, okay, I'm at neutral point. I can reduce, it's okay. But then these guys below down here, they're like, oh, I really rather not be reduced. I really prefer to be oxidized. So let's take a look at lithium on the bottom here, the most negative here. So it says here, the tendency for lithium ion to take that electron to turn back into lithium solid is really, really, really low. Now, if you think about it, group 1 metals always love to lose the electron to get lithium ion. So it's actually the reverse that's really likely to happen, right? It loves to lose the electron and turn itself into an ion. So lithium solid loves to be oxidized a lot, but lithium plus hates to be reduced. So that's why the reduction number is negative. Now, if you were trying to write the oxidation of lithium, so lithium solid goes to lithium plus an electron, the oxidation potential would be positive 0.34. So lithium, on this case, is being oxidized. If there's anybody else above it, it says, hey, I want to oxidize too. Lithium's like, no, I am the strongest at oxidizing, so let me do it and you can reduce. So anybody above it has to do the reduction. These guys cannot oxidize, so to do reduction, say if you pair iron 3 and iron solid with lithium and lithium solid here, so lithium will be like, well, you know, I really should oxidize, you should reduce because I'm really strong tendency to oxidize. So lithium is going to oxidize, and iron 3 plus is going to reduce to iron because it doesn't have the tendency to fight with lithium. So this one's going to be reduced. So the moral of the story is if you arrange the table in order, the top lines that are bigger numbers or more positive or less negative, right, the top is bigger, those are most likely to be reduced for it to be spontaneous, and the ones on the bottom will most likely be oxidized. So you have to write the reverse. Okay, so that's what happens in a voltaic cell. Top line will have to be reduced. Everybody below it that's paired with that top line will have to undergo oxidation. So if you pair F2 and F negative, let's say we pair it with gold, and it will be Au and Au3 plus. So F2 has to turn into F negative, and if you pair it with gold, the gold will oxidize Au going to Au3 plus. If you had to calculate the cell potential here, you would keep 2.87 because that's a reduction, and you would have to flip gold here to negative 1.5. So you take 2.87 plus negative 1.5 to get your E cell. Okay, so hopefully everyone's still following here. So that's an example of how to use our table here. Okay, so we talk about this here. So 0 is where the hydrogen was, right? So we want to remember these are standard conditions. When we do the Nernst calculation later, those are no longer standard. They're not 1 molar, they're not 1 atm. So the table values has a not sign because it's standard condition, okay? Now, see here, it says that the one that likes to be reduced will have a positive. The one that doesn't like to be reduced will be a negative value. So the one that doesn't like to be reduced, remember, those like to be oxidized, okay? So oxidation value is always going to be the opposite sign of what you see on the table, which is reduction. All right, so now that we have this here, let's go over some questions here and see if we can predict E cells or calculate E cells, okay? So here's a question. Oh, okay, I'll zoom out a little bit. All right, it says calculate E naught cell at 25 degrees. So it's all standard conditions for Al solid plus NO3 negative aqueous plus 4H plus aqueous goes to Al3 plus aqueous plus NO gas plus 2H2O liquid. Okay, so in this case here, we have, so I can see there's this right away. And then there's the nitrate and NO here. I know the hydrogen doesn't change. That's because I've done this many times. Is H plus, this is also positive one, that's negative 2. So the guy that's reducing is actually the nitrogen. Okay, so I would look for aluminum to aluminum 3 plus. And then I will look for nitrate going to NO. Okay, so that's what we want to look for. Now, who's being oxidized here? Can you tell just by looking if this is oxidation or this is reduction? Okay, so I have to look up the value from the table. You get oxidation number and reduction number, and then we get the total of it as E cell. Okay, we add these two up, and we get E cell. So let's take a look at oxidation, remember. So we are looking at all the reduction values, and we're looking for oxidation for aluminum. So that means the table, aluminum is all the way down here. So it's kind of small, so I'm gonna a little bit for you. So aluminum and aluminum solid, aluminum 3 and aluminum solid, that's what we're doing, right? 3. Yeah, we're doing 3. So in this case here, it says negative 1.66, but this is a reduction equation, remember? What we're doing is actually aluminum solid oxidized to aluminum 3 plus. So instead of negative 1.66, what do? We flip the sign, so we get positive 1.66. Okay, and then you look for nitrate and NO. Nitrate and NO, I don't see any nitrates here. Let me go up. Right here. See that? And that says positive 0.96. So let's do that. Remember, reduction you copy from the table, oxidation you have to flip the sign. Okay, so then we should be able to get our answer, put them together as positive 2.62. Now, this positive value here means it is spontaneous. And it's a voltaic cell. It will happen on its own as soon as you hook it up all up together. Okay, and if you hook it up to a wire with a light bulb, the light bulb will turn on. So that's one thing. So if your E cell is positive, it means it's spontaneous. If it's negative, it means it's non-spontaneous and it will be an electrolytic cell. If you wanted the reaction to work that way, you'd have to hook it up to a power source. Now, remember, one direction is spontaneous, the other direction is non-spontaneous. If you were trying to do the opposite direction, you would end up getting negative 2.62, just because the signs will be flipped around. Okay, so again, one more observation is you notice on that list there, nitrate was on the top, a bigger number, aluminum was on the bottom, a smaller number, and we flipped the bottom to oxidize it. So that's how you tell. The top line is a bigger number, it loves to be reduced more. The bottom line doesn't like to be reduced as much, so it'll be forced to oxidize. So you have to flip this aluminum down here, okay? So that's one question there. So we're just trying to construct it together. Let's try another one here. Here's a list that's already given to us so we can take a look at it. It says here, from this list of the reduction values, notice they were so nice. They have it coming down from most positive down to most negative in your short list here. Sometimes on the test, they don't give it to you in order. It's just a little jumbled up. So if you see the values not in order, try to arrange them in order if you had to tell who's oxidizing, who's reducing, okay? Because we always know for it to be spontaneous, the bigger number has to be reduced. The smaller one paired with it will have to be forced to oxidize. So IO3 plus H plus I minus going to I2 and H2O. So I see here I have IO3 and I2. So there's one. So there's one line here, okay? And then, so IO3, I2, right? Okay, and water. And then here's another one. You have I negative and I2 that I see over here. But you see how this one's flipped? So the top line is kept as is, and the bottom line is flipped. Okay? So I can tell just by looking, this is gonna be a spontaneous number. It's gonna be positive because we are flipping this guy and keeping that. So it's positive 1.2, negative 0.54. Add them up together, you will be able to get your E cell. Okay, so I'm gonna show you the next slide. It has to work there. So from the table, we looked up the values of these guys, right? We know the one that was flipped because that's, how do I know it was flipped? Because that's what the reaction said. The reaction was I negative going to I2. And I saw I negative on this side and I2 on the opposite. So I know that one was flipped. So this is a flip number, okay? The negative 0.54. And then this is what we have from the table, and you add them up together, you get your E cell of positive 0.66. All right, so with this whole oxidation and reduction thing, it's literally the same thing as finding if you is saying cathode minus anode, because cathode is the one that always has a reduction and anode is the oxidation. And if you put a minus anode, it actually turns into a negative sign. So it's the same equation, okay? But I like to see it as oxidation and reduction, so I know why I'm flipping things or why there's a minus sign there, okay? All right, so this is what we were talking about earlier. The top line has to be reduced, the bottom line has to be oxidized. So notice these two pairs here. There's copper and there's zinc, okay? These are both reduction values. And notice the copper has a bigger positive number than the zinc. The zinc actually has a negative number. So it really doesn't like to be reduced at all. It actually much prefer to be oxidized, okay? So because of this, the spontaneous cell will have copper turning to copper, copper 2 turning to copper 0. And it will force zinc to be oxidized. That would be your spontaneous reaction. So your spontaneous reaction will be zinc oxidizing, see that? Zinc going to zinc 2 plus, and copper reducing, copper 2 plus going to copper solid. So based on looking at the positions on the table, I can tell which one is a spontaneous reaction, and I know the opposite will be a non-spontaneous reaction. Okay, so now I want you, I'm going to write out some questions here, and you tell me if it's going to be spontaneous or not, and I'll give you the positions on the table. And I'll give you the values, okay? So let's go ahead and do that. First one we want to do together is Fe plus Mg2 plus going to Fe2 plus Mg. Okay, so we have to look on the table and look at these values here. Let's see, table values. Mg and Fe. Here's Mg. Mg is negative 2.37, and Fe was Fe2. So the Fe and Fe2. So notice there's. This one is going to Fe3. Don't use that one. You have to use the Fe2 one, okay? So magnesium is on the bottom here, negative 2.37. And then iron to iron 2 is negative 0.45. So the top one will be reduced. The bottom one will be forced to oxidize because it's more negative than the top, okay? So in this case here, I will say for it to be spontaneous, just by looking at the table, okay? Fe2 plus reduce to Fe, and Mg should oxidize to Mg2 plus. That's what I found on the table, okay? So for it to be spontaneous, and I said, well, if I wanted to, I can even calculate the E cell, because E reduction here from the table was, what was the number? The reduction from the table was negative 0.45. And then oxidation, we had to flip that number we saw. It was negative 2.37, so flip it will be positive 2.37. Okay, you would get 1.92. So this would be spontaneous. So is this reaction saying the same thing? Let's take a look. Iron is being oxidized. Magnesium is being produced. No, it's the opposite. Okay, so this one here, as written, non-spontaneous. Okay, and the cool thing is, since we calculated a spontaneous one, the non-spontaneous will literally be the opposite. It will be the negative sign. Okay, so because we would flip this to be negative, this would be positive. So it would be ESOL of negative 1.92. Okay, a lot of times they just ask you if it's spontaneous or not, so you don't actually have to calculate it. As long as you know how to read the table, you're good. All right, so let's give you a few more. So here's a few more. What if we paired I negative and zinc 2 plus? Would it be a spontaneous reaction, okay? So what if we paired calcium, and this is solid, and magnesium 2 plus? And what if we paired H2 and cadmium 2 plus? And we paired silver and 2 plus. All right, so we want to say, well, so this is I and this is zinc 2 plus, okay? So let's look for that. These are my reactants here, so that means it looks like I need to have I negative and zinc 2 plus on this. Let's see a kind of table for you guys. All right, so where's the table? I negative zinc 2 plus. I see, do you see I anywhere? I see a I negative here. It's over here though, okay? I negative and zinc 2 plus. I negative and zinc 2 plus. See that? Oh, you can't see. Maybe. I negative there, zinc 2 plus there. Okay, so the I negative line was on a, so they're saying, I want to take this and turn it into that because that's my reactant. And I want to take this and turn it into that because that's also my reactant. So these are my reactants here. Now, based on this here, I can tell they're trying to oxidize what's on the top because I negative going to I2 is oxidation. And they're trying to take zinc 2 plus and reduce it to zinc. Okay, so that means these guys are actually positioned in such a way it's non-spontaneous. Do we agree? Because if it were to be spontaneous, you should have written I2 solid and zinc solid as your reactants. Because this should be reduced, this one should have been oxidized for it to be spontaneous. Okay, so this one here, I negative zinc 2 plus will be non-spontaneous. Okay, let's check again. Now we want to check calcium solid and magnesium 2 plus. Okay, calcium, magnesium, I think they're both down here. Here's calcium. What was it? Calcium solid. So calcium solid and magnesium 2 plus. See? So magnesium is on the top and it says magnesium 2 plus is going to turn into magnesium because magnesium 2 plus was the reactant. Calcium solid was the reactant also. So it's going to go, this one's going to reduce, this one's going to oxidize. And that looks good because magnesium's on the top line, so it should be reduced. Oxidation is on the bottom line. Calcium should be oxidized. So that looks like it's a spontaneous configuration. Okay, so this one here looks like spontaneous. So you can actually just look at the reactants and you'll be able to tell. So H2 and cadmium 2 plus. So H2 gas. So it's this one. 0 and cadmium. Let's look for cadmium. CD, where's CD? Let's see CD. Here it is. So it was H2 and CD2 plus. So H2 and CD2 plus. No, this one's trying to oxidize this and reduce this. See that has the opposite side? That's not going to be spontaneous because it's is trying to oxidize on the top and reduce on the bottom. So that one will be non-spontaneous, okay? So let's write that down, non-spontaneous. Okay, the next one is Ag is an SN2 plus. So Ag, solid. Where's Ag? Ag is on the top. Ag is right here. Ag and SN2 plus. Okay, Ag is on the top right here, and I'm gonna scroll it down. SN2 plus is right here. So they want to take Ag as a reactant as SN2 plus as a reactant. So they're saying this is going to oxidize, it's going to reduce. That doesn't look good. It's not, it's the opposite of what it should be, right? So this one is non-spontaneous as well. Is everyone following so far how to tell spontaneous or not just by looking at these lines here? So non-spontaneous. So basically what you want to do is the top line, if N-E-O-U-S, the top line is more likely to be reduced, the bottom will have to be oxidized. Okay, very good. All right, so if we are good with that, what we want to keep doing is we want to continue. So here's a question that I want us to do together. Yeah, we can do this now. Okay, so so what we're gonna do is we are going to basically know how to calculate a potential, determine which way is spontaneous, which way is non-spontaneous. We just looked at a few examples, right? And actually can we do these, guys? Oh, there's more here. Let's do these real quick, okay? Let's do these first. Well, obviously I showed you the answer, so actually let me cover it. Let's pretend you can't see the answers. Okay, right there. Okay, and it says, decide if it's gonna be spontaneous, and this here is arranged in order for you already, okay? So we don't have to flip-flop to different pages, the tables right here. This says F2 and I negative going to I2 and F negative. So really you could have just looked at these two here. So F2 and I negative. F2 on the top, very good. It goes there, I negative going to I2, perfect. So this one looks like it's spontaneous because the top is reduced, the bottom is oxidized, okay? Spontaneous as written. Let's go to the next one. Magnesium and silver. I think we did this one. Anyway, magnesium's on the bottom. Magnesium is turning magnesium 2 plus. Silver is turning to silver solid. Oh, that looks good. Its top is reducing, bottom is oxidized. So again, this one's spontaneous, okay? Now, let's look at a third one here. Copper and iodide. So copper 2 plus going to copper solid, and I negative going to I2. Oh, so this one, you see how this on the top is going to the oxidized and bottom is reduced. So what is this one? This is the non-spontaneous version. If you calculated the E cell, you would have gotten negative value, okay? So they say it's spontaneous in reverse. Remember, it's the same thing as non-spontaneous as written. All right, another one here is copper and chromium. So these two lines here, it looks like. It's saying copper is going to copper solid, chromium 2 is going to chromium 3. So top is reducing, looks like, bottom is oxidized. Looks good. So it's spontaneous. Okay, so hopefully we are all good with this here, with trying to determine which one's spontaneous, which one's not. And actually, here's another question that's pretty cool. Let's do this one real quick before we go to the next part, okay? It says here, which of the following materials can be used to oxidize copper without oxidizing silver? So here's the question is, taking that same knowledge, but they're asking a little bit different. They're like, which one of these can oxidize copper without oxidize silver? So focus on the first line. Who can oxidize copper? So remember, if copper wants to be oxidized, so this is copper. Copper has to be below those guys, right? Copper wants to oxidize, so everybody on top will be reduced. So far, if you are just saying anyone can oxidize copper, these are all the potentials. For copper to be oxidized, I2 must be reduced, silver plus must be reduced, IO3 must be reduced, F2 must be reduced. Okay? But they said it has to oxidize copper without oxidizing silver. So they just narrow it down. They're saying it has to be oxidizing copper, so it has to be above the copper line, but below the silver line, because you don't want to be able to oxidize silver. Now, IO3 and F2 can oxidize silver, so those two are out of the question. And silver can't do it because silver is silver right there. So the only option here is I2 solid. Notice here there's I2 and I negative. So when it comes to that, you have to remember if copper is being oxidized, I2 must be reduced. So the answer is actually I2. Very good. Okay, so you'll see these on your practice or quizzes sometimes and on your practice exam. You want to make sure once you pick the line, you have to know if you're trying to oxidize the bottom, the top one has to be the one that's reduced. So you have to pick the reduced species that's being reduced. If you pick I negative, it's still wrong because you're saying I negative has to be oxidized. Okay, all right. So let's do the next question that I wanted to do. So here is what we have. Let me write out the question. Sketch and label a voltaic cell. Write the cell notation. So electrochemical cell notation, okay? And write full chemical equation. So we basically have to describe it using all the ways we've learned. We have to draw it out with the right cell notation, we have to write a chemical reaction, and all they give you is this. They say we have silver solid and 1 molarity silver nitrate. And then we have platinum solid and 1 molarity CrNO3 2 and 1 molarity, oops, I have my capital pen. CrNO3 3. So this is chromium 3 plus, this is chromium 2 plus, basically, because nitrate is -1, okay? So nitrate here obviously is our spectator ion here. So that's all you get. So based on what we have, we need to look up values from the table. Okay, so I'll bring out the table. We are looking for silver and are we looking for platinum? Platinum is in there, remember? We're actually looking for chromium 2 and chromium 3. We're looking silver and silver plus. And we have to decide who's being oxidized, who's being reduced, spontaneous. So the top line has to be reduced, the bottom has to be oxidized. Now let's look for silver. Silver was somewhere on the top, I remember, up here. The silver was right there. It was +0.8, I'll write it out in a second. Now we need to find chromium 2 and chromium 3. Chromium 2 and 3 is actually on the bottom here, see? So silver was on the top, it was +0.8, and then chromium 2 to chromium 3 was on the bottom, is -0.5. So if you wanted a spontaneous cell, chromium 2 should be oxidized to chromium 3 to give you +0.5, while silver is going to reduce to silver solid and just keep you at 0.8, correct? Okay, so I am going to write this down on my paper based on what I just discovered from the reduction potentials. I know that chromium is going to want to be oxidized. So my oxidation value for chromium was chromium 2 is going to turn to chromium 3. And then 1 electron, and my E of my oxidation was flipped from what was on the table, so it's positive oxidation, positive 0.5. In the table, it was a negative because it was a reduction equation, okay? And then the reduction part we'll just copy from the table. It was Ag plus electron turn into Ag solid. And your E of reduction was positive 0.8. So my E cell is positive 1.304. Okay, so this is spontaneous. So that's good because we were looking for a voltaic cell. All right, perfect. So now that we know who's being oxidized, who's being reduced, we can technically, we can write a cell notation. Okay, so the cell notation starts with anode and ends with cathode. Always remember that, okay? So who's my anode here? Anode is, actually, anode is, there's CO2, CR3, so it's actually, we have to use platinum. There's usually platinum here and CR2, CR3, so that's my anode. Now we'll draw a line, and then we have these two, so CR2 plus aqueous, comma CR3 plus aqueous, okay? And then double line, go to the next beaker. In the next beaker, I have silver plus aqueous, draw a line, and silver solid. Okay, I guess we should also say the molarity. I can put the 1 molarity here. That tells us the standard. So that's the cell notation, okay? And if you had to write a chemical, so we'll draw it later. Cell notation, then we'll write a chemical equation. So the chemical equation was, this is my reactant, this is my product. Can I combine? Yes, because it's 1 mole and 1 mole of electron. So my reactant is Cr2 plus Ag solid, Ag plus, going to Cr3 plus Ag solid. So that will be my chemical equation. All right, now we want to draw it. So to draw it, we'll have 2 beakers. Doesn't matter where the beakers are, you can put them wherever. So we can put silver on one side since they start with silver, whatever. So we'll draw 2 beakers, we'll do silver. This is my silver side, this is my platinum side, right? Or it really is a CR side. Okay, now I'm gonna draw a salt bridge. I didn't leave enough space, so. All right, and then we have to have the electrodes. This is when you see why we're in science, not in art class. Don't exactly have the really good talent of drawing. Okay, so we got a light bulb. Sorry, my light bulb's kind of lopsided. Doesn't matter, it still works. Okay. And this is the silver side, let's go with it. So I have silver ion in here. It's really silver nitrate solution, right? It's 1 molarity AgNO3. Don't need this parenthesis. And then you have 1 molarity of CrNO3, 2, 1 molarity of CrNO3, 3. So really, these two really mean they're Cr2 plus and Cr3 plus floating around. Okay? And then this one here is going to be my platinum solid, my cathode. This is going to be, one of those is my anode, my bad, anode. because it was oxidation. My cathode is silver. So anode is where oxidation happens. Cathode is where reduction happens. Okay, now remember anode is labeled as negative sign because platinum side here, the chromium 2 and chromium 3 is losing that electron. That electron is going to go all the way here and then go into this side because that 1 mole electron is going to be released over to here and it's going to be received by the silver side. Okay, so I'm going to draw the direction of my electrons going that way to the speaker, to the left. All right, so if this is negative sign, this must be a positive sign. Okay, now, so we know the direction of the electron, we know which one's anode, which one's cathode, we drew it out. The next thing is you have to put the salt bridge. So I'm going to use nitrate as my salt bridge because nitrate is a spectator ion. So I'm going to put a potassium or sodium, doesn't matter. So we'll do potassium nitrate here, okay, in my salt bridge. Now in the potassium nitrate, because the electron is leaving here, the nitrate ion should go in to the side that's anode because it's trying to balance out the negative charge. Put a negative charge since the electron negative is leaving. This one's incoming negative charge. So you want to make sure you help it out to balance the charges by making sure the potassium side comes in to help balance out charges. Okay, so that's how we would draw the cell here as a picture. So sometimes they give you a picture, sometimes they give you chemical equation, sometimes they give you cell notation. So it really depends. Sometimes they just give you this and then the table. You should be able to put them all together to decide how to get a spontaneous cell. Okay? So get a spontaneous cell. So, everyone good so far? All right, so based on this question here that we just did, I wanted to maybe use this table and we'll do something a little different. What if instead of just saying oxidize, what if they say something about reducing? Okay, so maybe we'll do the new question. It will be which one can reduce? So let's pick one. I2, but not reduce. Actually, I don't want to pick I2. Let's pick something higher up. Let's do AG plus, but not reduce CR3 plus. So you see how I can change the question to reduce and instead of oxidizing. And when I'm saying reduce, I'm referring to this line here and referring to this line here. Okay, so anyone below silver can reduce it. So I negative will be oxidized, so silver plus can reduce. Cu positive, Cu can be oxidized, so silver plus can be reduced. But if you don't want to do chromium, then you don't want to be below that. So magnesium won't be able to do it, and chromium's on the list. So the potential answers are this two, I negative or Cu2 plus for this question here. Okay, so I'll write down I negative or Cu solid. Those are my two potential answers. And then if this was the ABCD part, then I'll pick B as my answer. Everyone follow? So I'm just showing you different varieties of the questions. Okay, all right. There's no questions. We are going to keep going. Another cool thing is you can actually determine which metal will dissolve in what acid. Okay, now remember, when a metal dissolves, it's actually being oxidized. because the metal is a solid and metal's going to turn into a cation. It's always going to be oxidized. So basically, if you want to dissolve a metal, you have to make sure you use an acid that has potential that's above the metal. The reduction potential has to be above it, where the acid will take the reduction line and the metal will take the oxidation line. So the line for the acid should be above the metal when you look at it in order on a table, okay? So the common acid that we have is like H plus and H here. So actually have to flip off the pages. So in this case here, here's that picture. This is zinc dissolving in H plus, so hydrochloric acid is common, right? So the line for hydrochloric acid, let me show you that on the table, is right here, is this guy, H plus and H2, okay? So anybody below here, all these guys here, will be dissolving in hydrochloric acid, or actually even in acetic acid, because acetic acid also has H plus going to H2. So if you notice, zinc was on here. Zinc was, where is zinc? Zinc's right here. And then you have, remember if magnesium is the one that if you've done it, that one goes crazy, and that we do this one. Super reactive. We don't do group ones. So we try not to. Sodium is even more crazy, and lithium and potassium, they're like super reactive because they will dissolve and it's so hot, will like boil and pop and stuff. So magnesium already shows you that though. Magnesium's only over here. Anyone below it will dissolve even crazier. So in this case here, anybody, all these solids here, all these guys will oxidize when paired with hydrochloric acid, acetic acid, just acid has H plus. Now, one example that never dissolves in hydrochloric acid was copper. See how copper doesn't dissolve? Copper is above hydrogen. Can't dissolve because its tendency is for it to be reduced, but this guy to be oxidized. So it's not spontaneous. But you can force it to happen if you hook it up to an electrolytic cell. So if you can't dissolve copper in hydrochloric acid, they say use nitric acid. Nitric acid line is right here above. So nitric acid is this line above here with the NO3 one. And it's above these other guys. So nitric acid can take silver, can take copper, and those are the ones that wouldn't go in the other acids. Okay, so that's what on the slide here it says. Hold on, let me get to the page. It says almost. Well, if the metal is below the H, you can use it. If you can't, then we use nitric acid, right? Almost all metals will go in nitric acid because we're looking at the nitrogen, the nitrate part, right, in this line here, because it's a little higher than the H plus line. Okay, so the cool thing is, like, if you have silver and not silver, gold and platinum, these guys here are super hard to dissolve. You can actually use a combination of nitric acid and hydrochloric acid, concentrate at once, and if you soak it in there long enough, it will dissolve gold and platinum. Okay, all right. So here's a question. I gotta cover the answers up. So okay, it says, which of the following metal will dissolve in acetic acid? Oh, this is not, it was pen. So in acetic acid, this was the line we're referring to. Okay, so who can dissolve in there? Remember, it will be the lines below it. Now, so these are arranged in order already. That's why they don't have the numbers. If the table has numbers next to it and you see the numbers aren't in order, make sure you rearrange them first, okay? So H, and then everybody below it can dissolve. So magnesium will dissolve, chromium and iron will dissolve. Silver can't dissolve, copper can't dissolve, gold can't dissolve. Okay, so it says which one? So the answer would be iron and chromium, yes, no, and no. Okay, so the answer is C and D. Everyone good here? So it's at C and D, and then you wrote out the equations there. All right, so we're actually going to keep going here. Here is the next part. We actually still need to calculate other stuff. So based on what we know so far, spontaneous reaction, your delta G was negative, remember, delta G system negative. And then also we talked about S universe, and universe has to be positive. G is the opposite sign, so G has to be negative for it to be spontaneous. And then E here, we said that when it's positive, E cell is spontaneous. So we're putting this together. And also last chapter, we calculated when G was negative, your K is actually going to be bigger than 1 here. Okay, so let me show you that slide. Do we have that slide still? Hold on. So this was from the last chapter, okay? Remember this here? It says G is positive, K is smaller than 1, G is negative, K is bigger than 1, G is 0, K equals to 1. So that was this part here. Now this we just learned in this chapter. This one, these two we learned from the previous chapter. Okay, so those are spontaneous reactions. And then we also learned that delta G naught, when delta G equals to 0, equals to minus RTL and K. So we did this, right? Now we have a new equation here. Delta G naught is also equals to negative NFE. So we'll have to like know how to calculate that basically. So here's the link of all these values together. N is the number of moles of electrons here that when you want to make sure when you combine the two halves, you know the number of moles of electrons have to match. So that's the number of electrons there. F is Faraday's constant. It will be provided on your periodic table. So we learned this equation in a previous chapter. We learned this in a previous chapter. Well, no, we didn't combine with E, but we know the K and the G here. So now we want to combine these two here. We have a G and connecting into E cell, and E cell connecting into K. So these are our two new equations here. Okay, let me show you a bigger version of it. Right here. All right, so we are going to try to do problems that, we're not going to do this because we did this before. We're going to do these questions here, okay? And then obviously once we get to this part, we'll do the Nernst equation after that for non-standard conditions. But right now, let's focus on these guys first. All right, so the questions, let's try it. I2 plus 2Br negative, 2I negative, plus Br2 liquid. Is this reaction spontaneous? Find delta G naught. Okay, so I'll give you the values from the table, okay? E reduction from the table for Br2 with plus 2 electron goes to 2Br negative. E reduction for that guy is 1.09. Now the next line we have is I2 solid plus 2 electron goes to 2I negative equals. This E of reduction from the table is 0.54. Okay, so we need to see if this is spontaneous. So let's take a look. I2 going to I negative, I2 going to I negative, Br negative going to Br, Br negative going to Br. Just by looking, can you tell me it's spontaneous or not? We don't even have to calculate it yet. Can you see it's spontaneous or not? So it's saying I2 must go to I negative. Br negative goes to Br2, right? It's going to be non-spontaneous. Very good. Okay, so we can tell just by here saying they're non-spontaneous. The answer is no, big no. Okay, so let's work on it. So we gotta write out what they wanted. So E cell was E of oxidation plus E of reduction. So the oxidation it looks like is the Br line. This is my oxidation. The reduction line is here. Okay. I know this just by looking because these are ions and zeros. This is 0, -1, -1, and 0. So it's easy for me to tell what the oxidation states are. So oxidation, and plus I know that based on this here, I flipped the Br, okay? Because I flipped the Br, that's my oxidation, and it's positive on a reduction, so it's -1.09. Well, oxidation, okay? And then my reduction is going to be I2 going to I negative right here. So it's 0.54 S's. So that will give me -0.55. So that's how I also confirm it's non-spontaneous. Okay, now the next thing they say is find delta G naught. So delta G naught is negative NFE naught. And this E is E cell, okay? We just got the E cell right here. That goes there. But we need N. Faraday's constant is given, so we need to figure out how many moles of electrons. So can we tell how many moles of electrons here? So I can rewrite the, well, I'll rewrite it. Oxidation half is 2Br going to Br2 plus 2 electron. Reduction is I2 plus 2 electron going to 2I. So it's 2 and 2. Perfect, it matches. So my N here is going to be 2. Okay, so let's go ahead and plug it in now. That's a G naught equals to negative N, which is 2, from my 2 moles of electrons. I don't have to multiply my equations because they already match. And F is Faraday's constant is given. Moles of electron, coulombs, moles of electrons. And then you have your volts, right? So remember, volts is joules per coulomb. So I'm going to go ahead and write joules per coulomb there so you can see how it cancels out. And G is going to be in joules. So negative 0.55 joules per coulomb. Okay? So moles of electron cancel out, moles of electron, coulomb cancel out. All you have left is joules. So my answer in this case is going to be positive 1.1 times 10 to the power 5 joules. So that's really big. I can change it to kilojoules, so 10 to the power 2 kilojoules. Because you divide by 1,000 to get from joules to turn to kilojoules. So again, confirm it. Delta G is positive, so it's also confirmed again as non-spontaneous. Okay, all right. So that was this equation here. Let's do the one with K now. They're going to ask you to look for K in this case. Okay, so I'll give you the question. It says find K at 25 degrees Celsius. For this equation, Cu plus 2H plus going to Cu2 plus H2. Okay, we just talked about how copper doesn't dissolve in acid, right? I can tell you this reaction is non-spontaneous. Okay, but just by observation. But we can confirm that when we find the E cell and stuff like that too. But copper doesn't dissolve in regular acid. It can't, okay? So let's take a look at the table values. 2H plus 2E H2E of reduction from the table is 0.0. And then copper 2 plus 2E going to Cu is 0.34. So I'll put 0.00. Okay, so obviously my E cell oxidation in this case was copper. So copper 2 plus, oxidation is the opposite. So I'm just rewriting the equation out for you. Okay, so this is E of my oxidation. It should be negative 0.34. And then my reduction is just copy from the table. 0.00. So one important thing to remember, even if you had to multiply these guys to make your number of moles electrons match, never multiply your E cells or E oxidation reduction. These are intensive property. So E here, a reduction, and E naught plus M. E of oxidation are intensive properties. Do not multiply it if you multiply the reaction. Never do it. Okay, that's a very common mistake. Do not do it. Even if you multiply the reactions here, do not touch anything with the E oxidation or reduction. Those are intensive properties. All right, so we got these here, and then we can get E cell negative 0.34. So that's how I know it's non-spontaneous. Okay, now they ask you to look for K. You can relate E and K. E cell equals to, the equation was 0. So at 25 degrees, we can use 0.0592, okay? And log K. So we're gonna look for K here. Our N here is 2, so 2 and 2, they cancel out, perfect. So 0.0592 over 2 moles of electron. That's volts here. So, and then E cell was negative 0.34. So this is volts, 2 moles of electrons, and then log of K. So let's go ahead and do log of K on one side. Negative 0.34. And then we have to flip it, so 2 over 0.05592. Okay, so log of K equals to this times this term here, and I get negative 11.48. Okay, and then to get rid of the log, we take 10 to the power on both sides. So K equals to 10 to the power negative 11.48. And you get 3.3 times 10 to the minus 12. And again, remember, we predicted for something that's non-spontaneous, your K has to be smaller than 1, and that was true here. It's smaller than 1. Let's continue with Nernst equation. So where does Nernst equation come from? Well, it has to do with we're trying to find delta G for something that's not at standard condition, which means they're not going to be 1 molarity. Okay, so we got to see the equation between delta G and Q. We did this before. And then you don't have to know all this stuff. So they manipulated it by changing G and NFE, right? And then they used the RTL and Q in there. So they rearranged the equation. Okay, just based on this Nernst, well, this is where Nernst equation came from the delta G equation. Then we get the E equation. And plus, if you have 25 degrees Celsius, we actually plug in the temperature right here and have it come out to this number, 0.0592. So for our class purposes, we will be doing all our problems at 25 degrees on the test and the quiz, and I'm pretty sure on the homework too. But on the homework, just watch out if it's not 25 degrees Celsius, go ahead and put the temperature in here. And remember, you have to be using your Kelvin over there, okay? Because R here has units in Kelvin. So keep that in mind, but we're gonna be using this. So I'll put this equation actually, you'll see on the practice test that these equations, this one is actually on there. The more complicated equations I tend to put on there for you, okay? So check out the practice test, and we'll be working on a review as well. So we'll be working on this equation here today. So let me go ahead and show you a picture of what it looks like. So say if you have a standard condition, these are all 1 molarity, you would get 1.1, and that's what the table will give you from the reading. All the table values are standard condition 1 molarity. Now, if you ever change the molarity a little bit from 1, so this is 0.001, this is 2 molarity, it actually changes the number a little bit. So we're trying to calculate what's the little bit of difference there. And that's why we will use this. So this is the standard value from the table, and then the little bit difference from the standard, which gives you the actual E for the non-standard, depends on this value here. Okay, so we're gonna work on that. So let's try with first problem here. Let's write it up for you. So determine the cell potential for an electrochemical cell based on the following 2 half reactions at 25 degrees Celsius, okay? So it's 25 degrees, we're gonna use the 0.0592 equation here. So a lot of times they're not gonna say, hey, by the way, use Nernst equation. They're not gonna tell you. So you just have to look at the question and see, hey, if it's not 1 molarity, that's a good sign I'm using Nernst equation. So I'll show you the reaction here. Oxidation is Cu solid going to Cu2 plus equals 0.010 molarity plus 2 electrons. So that is a hint there, that's not standard. Reduction, MnO4 negative equals 2.0 molarity plus 4H plus equals 1.0 molarity plus 3 electron going to MnO2 solid plus 2H2O liquid. Okay, so we have our question here. All they give you is this. It says determine the cell potential. Here's the cell. Calculate what the cell potential is. So because it's not a 1 molarity, you will need to look up the values from the table, and you will also need to calculate what's the difference from the standard values. So the table values, remember, they're standard conditions. So I'm going to go ahead and write down these table values for you, and you would be provided these values on the test. On your homework on mastering, you will be able to click on the link to be able to pull up those values, okay, from a table. So E of reduction from the table, we have copper 2 plus 2 electron going to copper. This is standard condition because there's a not sign there. 0.34 volts, okay? And then we'll do the next one. We'll find the permanganate number. So it's MnO4 negative plus 4H plus 3 electron goes to MnO2 O2 plus 2H2O. The standard for this one is 1.68 volts. Okay, so in this case here, you have the standard value. You can actually calculate the E standard of the cell. Okay, so we know copper is being oxidized because they told us this. So copper is being oxidized, so you have to flip copper's number, right? So E cell standard is going to be, oxidation is negative 0.34 because this is E of oxidation, that's standard. And then plus E of reduction, that's standard, that's 1.68 right there. Okay, and you get your number there. That would be positive 1.34 volts. That's for standard. Now, you know this is not the answer because your things are not all one molarity, they're all different. So you have to calculate the difference. So how do you get the difference there? You use your equation E standard cell, well, E cell equals E standard cell, and it's minus 0.0592 over N, and then it's log of Q. Okay, so I want you to keep in mind the other equation, if you don't have the 0.0592, they kept it as natural log. So if you were doing a non-standard one, you can use the natural log equation. So let me show you again, okay? So this is the one, I'm not non-standard. If it's not 25 degrees, you use this equation here. Remember, you can look up Faraday's constant, you can look up gas constant. Everything else is like the normal. And this is natural log here, but the 0.0592 equation is actually for log log base 10. Okay, so that's what we have here. Now, let's go ahead and put this in. So we have to figure out number of moles, and we have to figure out Q. So we have to go back over here. Can you combine these two lines as is, like these here? You can't really do that, right? Because you have to have 6 electrons here, correct? And it's 2 and that's 3. That's not going to work. So you multiply the first line by 3 and multiply this one by 2. Then you should be able to combine them. Okay? So I'm going to go ahead and rewrite them multiplied out down here. Okay? So let's say we'll put a thing here. Say this one times 3, this one times 2. I'm going to rewrite it on the bottom here. So now oxidation looks like this. Cu. I'm going to skip writing the concentration. I'll just copy from the top so I have less to write. Equals to Cu2 plus, so it's times 3. So 3 Cu, 3 copper 2 plus 6 electron. Okay. And then my reduction is times 2. So that one's a little longer. Let's go ahead and write that out. 2 NnO4 plus 8H plus 6 electron going to 2 NnO2 plus 2H2O. Okay, so I just doubled everything and I tripled everything on top. Now I can say, well, these are all my reactants. These are all my products. So I can cross
Wouldn't it be 4H2O?
Oh yeah, that's right. Yeah, I did multiply by 2 and then I forgot this one. So this is 4H2O. Lucky for me, 4H2O is not going to be, even if I made this mistake, it's not going to be in my Q. So I actually would be okay making this silly mistake, but yeah, good catch right there. Thank you. So over here, now that we have this here, we know our N is 6. Okay, so that's 6 over here. I actually wanted to write this up because we needed these guys here for Q. And remember Q, we don't write solids or liquids. So this was a solid, that was a liquid. So we dropped that term. This was a solid, we dropped this term. We'll end up having some form of copper versus permanganate. Okay, so just remember, even though we multiplied this by 3 and multiplied this by 2, the standard value for the E of this oxidation here stays the same as negative 0.34. So I'm trying to remind you, this here is this intensive property. Even if you multiply the equations, it doesn't change the values here. A very common mistake is students try to start multiplying this value here and you get it all wrong. So do not ever multiply your E if you multiply your equation, okay? So I'll write it down here too. This is E of reduction standard. Still stays the same even if you multiply it by 2. This is 1.68 volts. Okay, so let's go ahead and write out the Q term. So remember, this is solid. We drop that. This is solid, and this is liquid. So all I have on my product for Q is, I'll write out N is 6 here. And Q is products or reactants. So these are not in there. This is my only product. So it's Cu2 plus. There's 3 of them. So I have to put to the power 3. And then this is aqueous and that's aqueous, so I need both of these on the bottom. So this is MnO4 negative to the power 2. And then it's H to the power of 8. H plus to the power of 8. So that's how you get your Q term. So notice this one's a little more complicated because there's 3 and 2 and 8 and there's 3 terms in there. But you already have all your values. And to get these molarities, remember the question gave these values to us already. So all you do is plug in the molarities there. So let me go ahead and rewrite everything again. So E cell now equals to E standard cell, which I calculated as positive 1.34. And then it's minus 0.0592, right? That's volts over N, which is 6. And then log of Q. So Q is copper to the power of 3. So copper was 0.010 to the power of 3. That was from the question. It's up here. Okay, and then you have permanganate is 2, hydrogen is 1, so I'm going to write that. So this is 2.0 to the power of 2, 1.0 to the power of 8. So that's a log. This is my Q right there. So put it in your calculator. You have to be careful putting all these things in. Your Q term here, I'll write it out. Q term ends up being 2.5 times 10 to the minus 7. So make sure you're able to get that. If you're not, sometimes if you're not doing it correctly, actually it becomes a problem if there's like scientific notation usually. I think without scientific notation, most of us can get it correct. So that's Q right there, and then you plug it in, okay? Your answer overall, we should get, let's see, 1.41. Okay, so it's, a little different at 1.34, but it's based off of that because of all the different new molarities there. So hopefully everyone is following that. Maybe we'll try one more just to see. Because, see, here's one form of the equation question. They gave you this part like that, right? Sometimes they actually give us an equation in scientific notation, not scientific, electrochemical notation. So I'll try that question so you can kind of see, sometimes they give you this type of equation, sometimes they give you the balance equation, and sometimes they just give you an equation with electrochemical cell notation. So let me go ahead and write that out for you. Here's our next question that we want to work on, just a different variety. Positive E cell is spontaneous. So this one here is positive, so it would be a spontaneous voltaic cell. Okay. And if you calculate your G, it would be negative. All right, let's go ahead and write the question out. Calculate the cell potential. the following reaction. At 25 degrees Celsius. So in the equation, the cell here is given like this. Mg solid, single line, Mg2 plus equals 2.74 molarity. Double line, Cu2 plus equals 0.0033 molarity. Single line, Cu solid. So that's another way of them asking questions. Sometimes they give you this. It's a little different, but it still tells you the same information. Okay, they're saying magnesium was oxidized, copper was reduced. If you know how to read the electrochemical cell notation, because this is my anode and that's my cathode. Okay, so based on this, I'm going to go ahead and write down the values for magnesium from the table. You will be able to look this up during homework. So these are reduction values from the table. Okay. On your test, you'll be given these values automatically. So Mg2 plus 2 electrons. They'll only give you the reduction, or they're not going to give you reduction and oxidation. So magnesium's value is negative 2.37. Copper's value is 0.34. We just saw that earlier. Excuse me. All right. So what we want to do here is we know this one's being oxidized, so we have to flip this guy. And this one here, we keep as is. Okay? Just by looking, they are flipping the one that's more negative, which if you were arranging them in order, this one would be on bottom. So this will be spontaneous, you can tell. Okay? But let's go ahead and do that. So E cell standard is E standard oxidation plus E standard reduction. Remember, oxidation is the one we flip, so that one, positive 2.37 volt plus 0.34 volt, just copy from there. So that number is going to give me E standard cell of positive 2.71. So that's my positive value. I know this cell is spontaneous, but this is the value if they were all 1 molarity. Clearly, these are not 1 molarity, so I need to use my Nernst equation to calculate what the actual E cell will be. So we need to find N and we need to find Q, okay? So let's go ahead and work on that. So the N here is easy because it's 2 and 2, right? So I'm going to go ahead and write it out, the equation here. We don't have to multiply anybody here, so that's nice. So oxidation is magnesium going to magnesium 2 plus 2 electron. And then reduction was copper 2 plus 2 electron goes to copper solid. So these are solid here. The ions are aqueous. So N here will be 2. Okay? So these are my reactants. These are my products. Oops, I forgot that. That was a really bad circle. Anyway, that's that. And then, so we want to find Q. Q here is product is Mg. So Mg 2 plus to the power of 1 over Cu 2 plus to the power of 1. So this is a simpler version because there's no like complicated multiplications, no coefficients. A lot simpler than the previous question, but you know, a little different because they give it to you in this form. So let's go ahead and plug it all in now to get our E cell at non-standard condition. So it's E standard cell minus 0.0592 over N log of Q. Okay, so that would be positive 2.71 volts minus 0.0592 over 2 log of Q. So we'll go ahead and put that value in. Magnesium's concentration from the question was 2.74. Copper was 0.0033. So that's my Q right there. And then overall, you should get an answer of 2.62 volts. Okay. All right. So let's continue with another form of Nernst equation. So we're used to doing these non-standard for different materials. Like here we have magnesium, we have copper, earlier we have permanganate, and what was it we had? Permanganate and copper. So it's just different materials. What if you use the same material? You can actually still do that. It's called concentration cell. So I want to show you a picture of it, and then we'll do some calculation, okay? So this is a picture of a concentration cell. We're still using Nernst equation. So the key here is to remember, if you were both using copper on both sides, if they were both 1 molarity, you know, basically one is negative 0.34, one is positive 0.34, because copper's value is 0.34. You would get 0 if it was standard. But if it wasn't standard, you actually get some other number that's close to 0, okay? So you can actually make a cell spontaneously flow if you change your concentration to be not 1 molarity. So what we're going to do is we're going to work on that calculation, okay? So they do tell you here a little bit more about concentration cells. It says electrons will flow from the electrode with a less concentrated solution to the electrode with a more concentrated solution. So even if you don't remember this, when you calculate, if you accidentally do it backwards, you just flip it around and you get the positive number, okay? So that's one thing that we will be working on. We'll do some calculation for that. And I'll draw it out to show you guys what it looks like, okay? So let's go ahead and work on a concentration cell problem. We're gonna do the copper, since it's pretty standard. So concentration cell. Okay, let's draw it out. So I'm gonna draw what we saw in the picture there. There's 2 beakers. And then both have copper in it. And then it's connected. And then there's I guess a light bulb if you want to make it light up. Connect this here. There's some electrolytes, and then you gotta connect the salt bridge. So in the salt bridge we'll put potassium nitrate. We'll use copper solid and copper solid. Okay, and then we'll do copper ion in here, copper ion in here. So it's like exactly the same, but the concentration is not 1 molarity for both. This guy's concentration is the smaller one, 0.010, and this guy's concentration is 2.0 molarity. Remember, we said the electron is going to flow spontaneously from the lower concentration to the higher concentration. So you can go ahead and write that out. So this is where the electron is flowing from the lower concentration to the higher concentration. So that means if the electron is leaving this side, this must be my anode side. And this bigger concentration side will be my cathode side. Okay, so hopefully you guys remember that. Now, if that's the case, if electrons are flowing in here, potassium actually has to go in here, and nitrate has to go in the smaller concentration to balance out the charge. Okay, so we have these concentrations here. So what we want to do is, you know, the value from the table. The table says copper 2 plus 2 electron going to copper solid at standard condition. The reduction value for this is 0.34 volts. If they were both 1 molarity and 1 molarity, it would have been 0, because one's positive 0.34, one's negative 0.34. Nothing would have happened. But something is happening here because the concentrations are not 1 molarity. Okay, so let's go ahead and calculate what the potential will be here. So oxidation and reduction. Okay, I'm going to rewrite it with the molarities now. So remember, we just said the smaller side is where the electron comes from. That's the anode side. Okay, so anode, which is oxidation. So oxidation would be the reverse, so it's copper solid goes to copper 2 plus, and I can go ahead and write down concentration. It's aqueous, and then it's 0.010 molarity plus 2 electron. And my E of my oxidation for this one is negative 0.34 for standard. If it was for standard, right? But remember, this is not standard here. I'm just writing the standard next to it. Remember, even if you multiply this, the value stays the same always. Now reduction is copper solid. Not copper solid, it's copper aqueous, 2 plus, and 2.0 plus 2 electron, and it goes to copper solid. So this E of reduction from the table would be positive 0.34. So if you just calculated standard, it would have been 0. Okay, but it's not standard, so you can do that. So E cell equals to E standard cell minus 0.0592 over N log Q. So again, we look for N, we look for Q, okay? E cell here is 0, standard is 0. Put that in, and then 0.0592 over N. So what's my N here? It's 2 and 2, so combining N is 2, okay? And combine acids. So circle that. That's my reactants. That's my products. Okay, so log of Q would be this guy, copper, right? So I'll go ahead and write the copper first. Copper 2 plus to the power of 1. And then the bottom one is the copper 2 plus to the power of 1, but it's 2 molarity. So this one here, we're going to do the products, right? 0.010. And down here is the reactant, it's 2.0. So that's how we get our Q there. So when you put it all together, you get a value. I mean, it's not 0, but it's a small value. This will be 0.068 volts. Okay, so gotta remember, if you see a concentration cell, anode is the oxidation site, which is the lower concentration. Okay, so that is pretty much the math stuff for the Nernst equation. I want you guys to just take a look at batteries. Now, batteries are all voltaic cells. So this is a voltaic cell because it's positive. Anything that E cell positive is a voltaic cell. That means you just put it there, it'll automatically do the reaction, automatically generate electricity for you. Okay, you can turn on the light bulb basically. So batteries are actually a form of galvanic cell, voltaic cell. There's so many different kinds. Just wanted you guys to, you don't have to memorize any of this, but it's really cool to be able to see like people come up with so many different varieties of batteries. Okay, there's the dry cell battery. You see how they have like different systems. You have anode, zinc or magnesium, so they put that in there. They pack it, so I mean, batteries are pretty portable, so they have to pack it so when they hook it up to the circuit, it completes. It can actually cause the reaction, the chemical reaction to happen, but because it's a redox reaction, you're actually completing the electrical circuit and generating electricity, and that's how things work. Okay, it's kind of cool. So they use cathode graphite rod, and then so there's the cathode here. You can see there's an anode somewhere in there, and they have a paste, moist paste. So I guess it's somewhat to be able to have contact so that they can still flow. Okay, so it's kind of cool. So that's one example, and there's a lot more examples on here. You don't have to worry about memorizing this, just appreciate that the batteries you use are all voltaic cells. Okay, so again, they tell you there's a different anode, different cathode, what's being oxidized, reduced, but you know, that's how basically you have batteries, okay, a voltaic cell. So that's the alkaline battery that we are used to. And then we got a lead storage battery. These are the car batteries. So what's in there? I mean, the common stuff. Look at this. You have H and SO4. So that's sulfuric acid right there. You guys see that? So there's lead oxide, lead sulfate. So, you know, that stuff definitely you don't want to play with. The electrolyte is actually a 30% concentration of sulfuric acid. So that stuff will burn you. 30% is strong, you know, like you don't want to mess with it. So that's the anode they tell you, and then this is for the cathode, what the reduction is. So it's kind of cool. You get to see, like, you know, what makes your car run, okay? And then we have nickel cadmium batteries, another type of battery. And then you have more batteries. And then what other batteries? Here's more lithium ion batteries. So you don't have to worry about memorizing this or stuff because every battery is different, okay? It's just that they all apply the voltaic cell concept. They put it together so it will have a chemical reaction, and when you complete it into the circuit, that's why you got to put the battery in the correct orientation, right? Once you put it in, it starts working, okay? So that's the idea there. So then they just tell you a little bit more about the batteries. There's overcharge tolerance and how much energy it generates. Don't really need to worry about all that, except that these guys are all going to be batteries, okay? So in this case here, and then we have fuel cells too. So fuel cells here, you don't need to worry about it. So there's, again, here we have anode reaction, cathode reaction, and it generates power for us too, okay? So that's all examples of our voltaic cells. Now, we want to talk a little bit about the opposite, so the non-spontaneous, which is not the voltaic cell, okay? So what we call the opposite of is electrolytic cell, okay? Electrolytic cells are non-spontaneous, okay? So voltaic cell is a spontaneous one that we learned before, where anode is where the electrons come from, and we show a negative sign because it leaves the anode, goes to the cathode, cathode has a positive sign, okay? Now, if you are doing an electrolytic cell, you actually have to force things to happen because it's not going to happen on its own. But if you wanted to force it to go the other direction, you hook it up to some external power. So they use an external electrical current here to force it to go the opposite way. Okay, it's spontaneous in one direction and non-spontaneous the other. So if you want to go the opposite way, you have to use some power to do that. So the last lab for electrolysis lab is actually, like, if you guys got to do it, just watch the video. It's super cool. Sometimes there's like side reactions happening. You make stuff that looks like alien material. It's kind of freaky. We actually don't want that to happen, but occasionally it happens and you get bad data, but it looks like a really cool thing. All right. But we actually hook it up to a little box of electrical current, and then we force the opposite reaction to happen. Okay. So, a little summary. In all electrochemical cells, oxidation always happens at anode. Cathode is where the reduction happens. Okay. In voltaic cell, we label the anode as negative side and cathode as a positive sign, because we know where the electrons come from anode goes to cathode. Now in electrolytic cells, we don't have the same label here, because what we do is anode is where oxidation happens still, but anode has to be hooked on to the positive terminal of your power source. Okay, so that is different. It's hooked up to the positive, okay? And cathode is hooked up to the negative, because you're gonna wanna force it to go the opposite direction, so you have to hook it up to the power source. Anode gets hooked up to the positive side, cathode gets hooked up to the negative side, okay? So voltaic cell is spontaneous in one direction here, so it's spontaneously want to go from zinc to copper. But if you wanted the opposite reaction to happen, you can do it. You just have to hook up a power source correctly. So you wanted this side to oxidize instead of naturally the opposite side being oxidized, you will hook the anode side you want to the positive side of your cell, your voltage source here. Okay, and then you hook up the cathode side to the negative side, and then you'll be able to force the opposite, the unnatural reaction. This is spontaneous, it'll happen on its own. You leave it as it will just go this way. If you wanted to force it the opposite way, you can still do it. Just gotta hook it up to the battery source correctly, okay? So here's examples of electrolysis. Again, don't need to worry about all these examples like the batteries. I don't want you to memorize every single one, but sometimes the extra credit stuff, they'll kind of ask you questions on it. So make sure you can refer to it, but don't worry about it showing on your test because you don't need to memorize all the different kinds of batteries and electrolytic cells, okay? So here's some slides on electrolysis cells, and basically remember, it's trying to force the opposite from happening, okay? Spontaneous is voltaic, the non-spontaneous is trying to force it to go opposite way, so it's going from here to here. You have to use electrolytic cells. So there's applications here to say extracting metals, production of H2 fuel cells, metal plating. So all these here, we don't need to worry. It's just all the stuff I mentioned earlier. So here's some examples. So here, electrolysis of sodium chloride. Molten, it's liquid, it's not the aqueous kind. It's like you actually take the NaCl and you melt it. It's a really, really high temperature. And then you have electrolysis of water. Okay, here's another example. So there's actually in-home experiments that you guys can do if you wanted to, have some fun at home. You can actually split water on your own and trap your oxygen gas and hydrogen gas in little balloons. Of course, if you really wanted to try, you can do some flame tests, but I don't think you generate that much hydrogen or oxygen gas to be worried about it. But it's kind of cool. You'll be able to see your gas coming out. You use like plastic cups and little push pins as your electrodes and stuff. So it's kind of cool. Look it up if you guys are interested, okay? And so here's electroplating. We will be doing some calculations with electroplating. It's pretty simple. It's just stoichiometry stuff. So I will show you guys a few questions on that electrolytic stuff, okay? So this is a calculation part. The things you need to remember is some stuff we mentioned before. 1 amps is 1 coulombs per second, okay? And 1 mole electron is 96485. And on the periodic table, you actually get 96500 coulombs of charge. It's Faraday's constant. This is F. So you'll be provided these values, but you have to remember amps is coulombs per charge, okay? So let's go ahead and try some questions here. All right, so it says calculate the mass of AU, which is gold, that can be plated in 25 minutes using 5.5 amps for the half reaction. So they give you the gold half reaction. So it's gold 3 plus 3 electrons going to gold solid. So this is gold plating, like saying like how many grams of gold can you plate in 25 minutes if you use this amps for your current. And this is 3 electrons per 1 gold. Okay. All right. So here's the thing I like to do. It's basically like putting things together. So there are formulas if you wanted to look at your lab equations. They give you formulas, but sometimes memorizing, and I don't like to memorize formulas. So if I don't have to, so I like to go ahead and just list out all the information they gave me. Okay. So what did they give me? The time is 25 seconds and 25 minutes. So time is 25 minutes. I can write it out. And then I can see that amps here, the current is 5.5 amps, okay? And that is the same as 5.5 coulombs per second. And since I'm seeing seconds here, I might as well just go ahead and change this to seconds. So 25 minutes turns to seconds. Well, to do the conversion, correct? So it means 1 minute has 60 seconds. And then you just take 25 times 60, but we'll work it out in the math together. So I see there's a connection between seconds and coulombs. Okay, what's my ultimate goal? I am looking for grams of AU. Okay, so another cool connection is you need to see that coulombs here is can be linked together with moles. Okay, so we use Faraday's constant. So F here is Faraday's constant is 96485 moles of electron. Moles of electrons at the bottom is coulombs per moles of electron. So per mole, so I can just put 1 mole of electron down here just to kind of hopefully see it. Okay, so I can actually say, well, I have seconds. I have seconds related to coulombs, so I can do my calculation there. Because technically, if there's coulomb per second, you can just put this and say 1 second on the bottom. Okay, that's what I like to do. 96485 coulombs per mole electron, I put the 1 on the bottom. So you can kind of see the connection there. Okay, and then, so I just basically link from seconds to coulombs to moles of electrons. Well, over here, I have moles of electrons to moles of gold. So I also know that 3 moles of electron is going to link to 1 mole of gold. Solid, okay? Based on that right there. And then all I have to do is look up the molar mass of gold. So molar mass of gold from the periodic table, you'll be able to see it, is going to be 196.97 grams per moles. So you just saw that we can go from seconds, then get to coulombs, then get to moles of electrons, and then moles of gold, and then grams of gold. Okay, so that's how I like to put pieces together. I just like to write everything out and see how they connect. I just find the units that link together. Okay, so my idea is 25 minutes is starting, and I need to convert it to seconds. So I'm going to draw a little long one right here. So 1 minute is 60 seconds. So that's why I knew that I had to multiply by 60 to get my seconds. And then I'm going to go from seconds. I'm going to turn it into coulombs here. So my seconds go on the bottom, 1 second per 5.5 coulomb. Okay, so that part now I have coulombs. And then I want to link coulombs to moles of electrons. So I can't put the coulombs on the top because I have to put the coulombs on the bottom here to cancel it out, but that's okay. Just do that. This is dimensional analysis. And then 1 mole of electron is on the top here. Okay, so now I have moles of electrons, and I know 3 moles of electron is to 1 mole of gold. So I write down 3 moles of electron to 1 mole of gold. And then all I do is do the molar mass. 1 mole of gold weighs 196.97 grams. That's how I will get the grams of gold. Okay, so it's basically seeing what information they gave you, remembering to use Faraday's constant, and remembering you use half half equation that they gave us here, and that amps is coulombs per second, like little things like that. Okay, so put it all together, you'll find out that you can actually plate 5.6 grams of gold in 25 minutes. Okay, for this question. So the reason why I don't like to memorize is because they always ask the questions in many different forms. So then the equation will keep changing. I don't like that. I like to be able to map it out on my own. Okay, so here's another question. It says here, calculate the amperage, so how many amps required to plate 2.5 grams of gold in 1 hour. Okay, so now they're asking you to find amps, which is find coulombs per seconds. So can you find seconds if you have hours? Yes. So that's one thing you want to think about. I'm going to take 1 hour and convert it to minutes, convert it to seconds, and then that's going to go there. How am I going to get coulombs? Well, I have 2.5 grams of gold. I just calculated grams of gold from time earlier, so I should be able to figure it out, right? So I have 2.5 grams of gold here. Use the molar mass, you can get moles of gold. Correct? And then we also remember that gold here is 3 electrons, right? So moles of electrons can go there. So using molar mass, and this is 1 mole of gold to 3 moles of electron, right? So we have moles of electron there. And then once you have moles of electron, you can always link it to coulombs using Faraday's constant. So I have that part. Now, that goes there. And then your seconds comes from there. So you put those two together, you should be able to get the amps. Okay, so let's go ahead and try it out. So 2.5 grams of gold. Use the molar mass. So 1 mole of gold is 196.97 grams. And then we'll do moles of gold, we'll do moles of electrons. So Faraday's constant. So oh yeah, we gotta do this one first before we do Faraday. So 1 mole gold, 3 moles electrons, and then we do Faraday's constant. So 96485 coulombs, and the moles of electrons is on the bottom, which is 1. 96485. So I should get my coulombs right there, and then I'll put the coulombs on the top. So the coulombs there is 3670 coulombs. Okay, and technically you only keep 2 sig figs. This is exactly 3 and exactly 1, so these are exact numbers. That's an exact number, 1 mole and 1 mole here. So the smallest limiting is this sig fig here is 2 sig figs. Okay, then we gotta also consider 1 hour, so 1 hour. We want to turn it into seconds. So it's really times 60 and times 60, but I'll work it out, show you. 1 hour has 60 minutes. 1 minute has 60 seconds. And then you get 3,600 seconds here. I guess, you know, ideally the question should have done 1.0 hours. Let's do that. 1.0 hours. So you get 2 seconds there. Okay, and then let's put them together. The amp you need is 3670 coulombs over 3600 seconds. So you get 1.0 amps. Okay, so let's try one more version, okay? So we want to do how long, now we're going to calculate time. How long must a constant current of 50.0 amps be passed through an electrolytic cell containing copper 2+ ions. So they're saying copper 2+, that means there's to turn into copper solid, there's two moles of electrons there. It's a hint, okay? Copper 2+. To produce 5.50 moles of copper metal. So that's copper solid. And then it says give answer in hours. So when you calculate this, it's going to come in seconds, and then you can convert it to hours. So what we want to do is let's write down what they gave us, okay? They are looking for time, so we want to get seconds somehow, and then from seconds we'll turn it to minutes, and we'll turn to hours. But how in the world do you get the seconds? So let's see what they have. We have this 50 amps is 50 coulombs per 1 second. Okay, we know that. And then we also know that 1 mole of copper is to 2 moles of electron because it's 2 plus here. We know that. We also know we want 5.5 moles of copper. Okay. So there's moles of copper. You can link to moles of electrons, right? And then how do we get from moles of electrons to coulombs? We'll use Faraday's constant. Faraday's constant is 96485 coulombs per 1 mole of electron. So then we can link moles of copper to moles of electron, and moles of electron to coulombs, coulombs to seconds. And then once we get seconds, we'll go to hours. Okay, so that's what I'm going to do. That's my plan. I'm going to start with copper. So 5.50 moles of copper. And then what I'm going to do is moles of copper to moles of electrons. So 1 mole of copper, 2 moles of electron. And then we'll do electrons to coulombs. So 1 mole of electron is to 96485 coulombs. And then I can do my coulombs to seconds. So 50 coulombs per 1 second. And now I can turn from seconds to hours. So 1 minute is 60 seconds. 1 hour is 60 minutes. So my answer will be in hours. Okay, so put all that in there and you will get the answer as 5.90 hours. So that's what we want the end of chapter 20 here. Okay, just learning to calculate electrolytic calculations basically usually is plating of metals. Okay, so we have 3 different examples here. That's the end of electrolytic stuff. So not too much. Okay, so you should be able to do all your homework questions for chapter 20. Now, let's take a look at what I want you to remember from chapter 21, okay? So that's 20 is over. So chapter 21 is nuclear chemistry. So because we are kind of needing to, finish our material, just wanted to show you that we're going to talk about radioactive stuff. But the most important thing is I want you to calculate stuff that has to do with the half-life of radioactive stuff. Half-life, the time, and all that decay, basically, okay? So let's take a look. You have isotopes, okay? We have isotopes, like, what are isotopes? Isotopes are same number of protons, different number of neutrons, right? So here's some example. So under magnesium here, you have a stable isotope is 2412. And then the radioactive isotope is 2312 and 2712. So 12 tells you it's magnesium because on your periodic table, if I can find a periodic table, I have one somewhere. Actually. I'll just use my textbook. So periodic table here. How do we know magnesium is 12? Because it's the 12th thing on your list. Where's my periodic table? Okay. So you see 12? That's magnesium. Okay. So whatever the bottom number is, the atomic number that tells you what element it's going to be. Okay. So you just keep that in mind. And then they tell you, so if you looked at iodine, iodine has number 53, so it's the 53rd one. So if you look on for iodine, it's right there. See, it's 53? So that's the number of protons. So because it's 53, it will be labeled as iodine. but they have different numbers of neutrons. So this one's 127 is a stable one, 125 is not stable, 131 is not stable. The ones that are radioactive are not stable because they can decay and change into different isotopes, okay? So, and then uranium has no stable isotopes, they're only radioactive ones, but uranium's number is 92. So if you want to look, 92, number 92 is where uranium is, so you just look for 92, so it's right here, okay? And then these are the isotopes that they have. So how do they decay? Well, they radiate into different forms of stuff. There's alpha particle. So the symbol for alpha particle is 4,2 helium. Okay, this it basically loses a helium. 4 total is a neutron and proton, and 2 is for number of protons there. Okay, so they tell you, remember the mass number and the charge. So that's like basically what this is, okay? And then you have beta particle is 0 and -1. So it's kind of like it's basically an electron, right? It says -1 here. The charge -1 doesn't have a mass. We have positron, positive charge. And then we have gamma is 0, 0. We have proton. You can have proton is 1 and 1. And then you have neutron. So these are the common forms of radiation. Okay, so these will be useful when you're doing your extra credit stuff, okay? So here's alpha particle, beta particle, positron, gamma ray. So a lot of times, like, you just basically memorize what these guys are. Because once you have this here, you can actually write equations. Okay, so remember we talked, the bottom is the atomic number, top is the mass number, neutrons and protons, and then the symbol. The symbol is dictated by the number down here, okay? So the key here is to remember all the numbers on the top add up together, all the numbers on the bottom add up together. So if you said, I want CF here, 25198 to turn into, to release a helium, 42. So this is alpha particle. So you gotta make sure 251 has to -4, so you get 247 here, because the top has to add up to 251 still. And then the bottom has to add up to 98. So you should do, since there's 2 here, you gotta make sure it's 96. So it turned from 98 to 96. So you look here and it says 98 is CF here, 96 is CM. That's why it changed there. So all you do is you need to be able to understand these, why they're changing. It's because of the atomic number changing, okay? So you just gotta make sure that top adds up, the bottom adds up, and it all balance to the same number. They show you different examples of decays. You'll be able to see all this if you do the extra credit, okay? If you're interested. So when they say, see here it says write the equation if you want to do a beta decay. So you need to find out what a beta particle is, right? So beta particle is 0 and -1 if you memorize that, or look it up from the list. I'm not really going to test you guys on this. It would just be an extra credit homework. I will test you on the calculation part, which I'll show you later. So because it's 0, you can keep 60 on the top. But because it's -1 here, you have to make sure it's 28 on the bottom. So make sure both sides add up to 27. So it does change from cobalt here to nickel because the number of protons there change. Okay, so that's the idea there. Now, the most important thing here is, here's more, there's gamma, radiation, positron, emission, same thing. They just, basically the top adds up, the bottom adds up, okay? Same idea there. And then another, this is the table, like a lot of people, if you memorize this, you can do all the equation writing easily. Now, what I want you guys to focus on is this, the half-life stuff. Remember the half-life stuff? We did this in chapter 14, is it 14? No, 15. Yeah, we started at 14. So we did this in chapter 15. So it's kinetics, okay? Just remember, all radioactive stuff is first order. So basically we'll be doing first order calculations of radioactive material. So I want to do a few questions here with the radioactive stuff. I'll just do a couple today. And then we'll be able to do, those are the stuff that you want to be concerned about. You'll see on the practice test as well, okay? So let's go ahead and do some half-life, first order problems. And remember, remember those equations are given on your periodic table anyway. So here's one, but they're not going to tell you first order now because you need to remember all my radioactive stuff is first order. So the nuclide AS76 has a half-life of 26.0 hours. If a sample of AS76 weighs 344 grams, what mass of AS76 remains after 5:38 minutes? Okay, so this is stuff we've learned before, except now they go to the point where they don't even tell you it's first order. Okay, but you gotta know all the radioactive stuff is first order, okay? So, first order equation is Ln, remember Ln AT, if you don't remember, it's on your periodic table, okay? Minus KT plus Ln A naught. Okay, so it says if a sample weighs 344, so 344 goes in my A naught. That's the original. Okay, you're looking for AT because what mass remains, and the time is 5:38 minutes. Now here's the trick. There's half-life here, but half-life isn't in the equation. But remember, half-life is linked to K because it's Ln2 over K here. Okay, or you can say K is Ln2 over half-life. Okay, so this is the stuff we learned from a while back. So it's just a review, okay? Now, we will put this in here. Now, you have to remember this is in hours, this is in minutes. You have to make sure your units are consistent. Pick one, right? So I like to go ahead and we can just say, we'll take 5:38 divided by 60, turn into hours. So our time here is going to be 5:38 minutes. And then 1 hour is 60 minutes. So that would give us the new number. Okay, I actually don't even like to calculate this. We can, but I actually like to put this straight into my equation, in my T. Let's go ahead and find that number anyway for now. I don't round it. I like to keep everything on my calculator the whole way through. So 5:38 divided by 60. So you get 8.96667, so it's a lot of stuff, so I'll just round it up. And really, you just keep 3 sig figs. These are exact numbers, so they're not going to be used for your sig figs. You follow this guy, okay? Because 1 hour is exactly 60 minutes. So I actually keep this whole term in my calculator. I don't round it, okay? So we keep that in mind. So let me go ahead and rewrite it. So I'm looking for LNAT, and minus K is this. So it'll be Ln2 over my half-life, which is 26.0 hours, plus, that's K, and then T. And T is this one here, hours. But I'm just going to write this down here. So it's really 5:38 divided by 60 hours, right? You just did that. So that way I don't have to round. And then plus Ln 344. Okay? So once you put all that in, you should be able to get a term over here. That should come up to 5.6. And that's Ln at time t, which is the time of 5:38 minutes, or 8.97 hours. So to get rid of Ln, we take E on both sides. So AT is what's left over at that time. So what's left over is 271 grams. E to the power of 5.6. Okay, so that's one example. And you'll be practicing, and a good practice is to go back in that chapter and focus on this. And you should be able to find dynamic study watching all this stuff too. Okay, let's do one for carbon. Okay, so carbon 14 has a half-life of 5720 years. This is a first order. That's so nice. They told you it's first order. Okay, so half-life is 5720 years. It's a first order reaction. And it says if a piece of wood has converted 25% of carbon 14, how old is it? Okay, so how old is it? Well, we just have to find the T basically, okay? So what's the equation? ln AT minus KT plus ln A naught. So I know the half-life. So I know K is ln 2 over 5720 years. Okay, because it's ln 2 over half-life from this equation right there. Okay, we have that part. What time is that? We're looking for that. And it says it converted 25% of it. So original would be 100%. Okay, so I'm going to go ahead and write it out. So minus K is ln 2 over 5720 years. And then T is what we're looking for. ln, I'm going to go ahead and put 100 because we start off at 100%. And it says if it's converted 25% of it, what's left over at this part here? This is how much is left over at that time. So if you converted 25 of it, you have 75 left. You have to remember to put 75 in there. Don't put 25. If you read it wrong, put the wrong number, you'll get the wrong answer. Okay, so this is 75 that goes in here. Then we just solve for T, okay? So to solve for T, you can put all these and turn it into numbers if you want. You can do ln 75 minus ln 100, and then you do this term. So it's algebra, okay? So minus ln 100, so ln 75 minus ln 100. That would be negative T. Actually, let me flip it around. Let's make it positive. Flip this over here and that goes there, okay? ln 100 minus ln 75, because I'm going to go ahead and turn this into a positive. So actually, let me write it slowly so you can follow. So now I have ln 2 over 5720 years here. Okay, so all I did was just did that and then that one over here. I switched two things at one time, okay? Now once I have that, I can do that, whatever you do that in your calculator, and then I have to put this on the other side. So multiply by 5720 divided by ln 2, okay? And you should get an answer of about 2374. Really, we only keep 3 sig figs technically because this is 5720. We don't know if this is significant, but it's about there.